Over 4.6 billion years ago, before there was life, before oceans, continents, or even atmosphere, the Earth began as a violent, chaotic mass within a swirling disk of dust and gas surrounding our newly formed Sunday. This was the Hadean Aeon, the very beginning of our planet's story. Named after Hades, the ancient Greek god of the underworld, the Hadean was a time of hellish conditions, extreme temperatures, relentless impacts from asteroids and comets, and a surface more like a sea of molten lava than any solid land we know today. And before we continue, please subscribe and leave like for more sleepy science videos. In the earliest moments, gravity pulled together particles of dust and rock, slowly building larger and larger clumps through a process called accretion. These clumps collided and fused, their energy released as heat, until a growing proto-Earth took shape. The planet was completely molten at this stage, with heavy elements like iron sinking toward the center to form the core, and lighter silicates rising to the surface to form the primitive mantle. This process, known as planetary differentiation, laid the groundwork for Earth's internal structure: the iron core that generates our magnetic field, the mantle that drives plate tectonics, and the crust we live on today. But the early Earth was anything but stable. Around 4.5 billion years ago, a Mars-sized object, likely another protoplanet named Theia, collided with the young Earth in a cataclysmic impact. This was one of the most significant events in Earth's history. The force of the impact was so immense that it vaporized part of the Earth's outer layers and ejected massive amounts of debris into orbit. Over time, this debris coalesced into a new celestial body, the Moon. The formation of the Moon not only stabilized Earth's axial tilt, helping to regulate our seasons, but also affected tides and long-term climate patterns, becoming a constant companion in Earth's evolution. As time passed, the surface began to cool. Crustal rocks slowly solidified from the molten mantle, forming the earliest primitive crust. However, this crust was continually destroyed and reformed by constant asteroid bombardments and intense volcanic activity. Massive plumes of magma broke through the surface again and again. The Earth was still hot, radiating leftover energy from its formation and continuously heated from the inside by radioactive decay of elements like uranium and thorium. The early atmosphere, too, was hostile. It wasn't anything like the breathable air we have today. There was no oxygen. Instead, it consisted mainly of hydrogen, helium, water vapor, methane, and ammonia, gases released by volcanic eruptions or delivered by incoming comets. These gases helped trap heat, making the already searing environment even more extreme. There was no ozone layer to protect the surface from the sun's deadly ultraviolet radiation, and no stable land masses, just a fiery, unstable world. But hidden within the chaos were the seeds of something extraordinary. Around 4.4 to 4.3 billion years ago, Earth's surface cooled enough for liquid water to exist. Some scientists believe that water arrived via icy comets and asteroids that bombarded the planet, while others argue that it outgassed from Earth's interior during volcanic eruptions. However it got here, the arrival of liquid water was a transformative event. It filled massive basins and cracks on the young crust, forming the first oceans. These early seas would become the cradle for life much later. But in the Hadean, they were merely pools of boiling, acidic water under a heavy, toxic sky. During this time, Earth also began to develop its magnetic field, generated by the movement of molten iron in the outer core. This magnetic shield, weak at first, would grow stronger and become essential for protecting the surface from the sun's solar wind. Without it, Earth's atmosphere might have been stripped away entirely, as happened on Mars. The magnetic field, combined with a thickening atmosphere and growing oceans, marked the first signs that this planet could eventually harbor life. There are no known rocks from the Hadean Aeon that remain intact today, Almost everything from this era has been recycled by plate tectonics or destroyed by impacts. But tiny zircon crystals found in ancient sediments give us clues. Some are over 4.3 billion years old, suggesting that solid crust and even oceans may have existed far earlier than once believed. The Hadean Eon didn't last forever, but its violent legacy shaped every part of the Earth's identity. It created the moon, forged the magnetic field, formed the basic structure of the planet, and possibly delivered the first water. Though life had not yet begun, every essential condition for life was being prepared. The Hadean was the Earth's fiery infancy, brutal, raw, and foundational. It ended around 4 billion years ago, giving way to a new era, the beginning of Earth's geological record and the earliest signs of life. As the Earth entered the Paleoproterozoic era, approximately 2.5 billion years ago, it was already a world transformed from the molten chaos of its birth. The surface had cooled enough to support stable continents. The oceans were vast and saline, and the sky, while still hostile by modern standards, was thick with clouds and rich in volcanic gases. But something unprecedented was about to unfold, something that would change the chemistry of the atmosphere, reshape the biosphere, and ultimately make complex life possible: the rise of oxygen. This era is most famously marked by the Great Oxygenation Event, a turning point in Earth's history that would reverberate for billions of years. Long before animals or plants ever existed, Earth was dominated by microscopic life. Among these ancient organisms were cyanobacteria, simple, single-celled beings that performed a revolutionary type of photosynthesis. By absorbing sunlight and using carbon dioxide and water, they produced glucose for energy. But they also released a waste product: oxygen. At first, this oxygen had little effect on the atmosphere. It was rapidly absorbed by iron in the oceans and crust, reacting to form rust and settling on the seafloor as iron oxide sediments. But after millions of years, these chemical sponges began to saturate. The excess oxygen started spilling into the oceans and then into the air. To us, oxygen is the very symbol of life. But to most of Earth's ancient organisms, it was toxic. Anaerobic life, those microbes that thrived in an oxygen-free world, faced a deadly crisis. For them, this changing atmosphere was not a gift, but an extinction event. Entire ecosystems vanished as the oxygen concentration rose. This period of biological catastrophe is what gives the Great Oxygenation Event its name. It wasn't just a geochemical shift, it was a mass extinction, wiping out countless anaerobic species that had dominated the planet for billions of years. At the same time, this new oxygen-rich environment set the stage for future complexity. For the first time, Earth's atmosphere contained enough oxygen to begin forming ozone in the upper layers. Ozone, a molecule made of 3 oxygen atoms, created a protective barrier against the sun's ultraviolet radiation. Before this, any life near the surface of the ocean or land would have been exposed to lethal rays. With the ozone layer slowly forming, the stage was being set for organisms to eventually move out of the deep ocean and colonize the shallow seas, and, much later, the land. The Paleoproterozoic was also a time of tectonic shifts and continental growth. Earth's first supercontinent, called Nuna or Columbia by some geologists, began to assemble during this era. Massive plates collided, giving rise to towering mountain chains that slowly eroded over time, depositing sediments into ancient basins. These processes were the first large-scale geological cycles similar to what we see today. The Earth's crust had matured to a point where the rock cycle, plate tectonics, and continent formation were actively reshaping the surface. This dynamic activity not only influenced the landscape, but also affected ocean currents, atmospheric circulation, and the chemical composition of the oceans, all of which, in turn, impacted life. Within this evolving environment, Another remarkable milestone was reached, the emergence of eukaryotes. Unlike simpler prokaryotic cells, which lack internal compartments, eukaryotic cells possess nuclei and organelles, structures that allow for more complex functions and specialization. It's believed that eukaryotes evolved through a process known as endosymbiosis, where one cell engulfed another, and instead of digesting it, formed a symbiotic relationship. The engulfed cells became mitochondria, the powerhouses of modern cells. This evolutionary leap enabled organisms to become larger, more efficient, and more capable of specialization, laying the groundwork for all multicellular life to come. The world remained dominated by single-celled organisms, but their structure was becoming more complex. Stromatolites, layered structures formed by cyanobacteria trapping sediment, flourished in shallow marine environments. These structures, some of which still exist today in isolated environments, are among the oldest fossils we have, offering a direct link to the microbial life that once ruled Earth. Climate during the Paleoproterozoic was far from stable. Some evidence suggests that Earth may have experienced brief glaciations, possibly even the first snowball Earth events, where ice reached the equator and the oceans froze over entirely. While not as extreme or global as those that would occur later, these glaciations were signs that Earth's climate system was becoming more sensitive and complex, driven by both geological and biological feedbacks. As the Paleoproterozoic era came to a close around 1.6 billion years ago, Earth had already undergone a monumental transformation. From a planet choked in volcanic gases and ruled by anaerobic microbes, it had become a place of dynamic geological change, atmospheric oxygen, and the first complex cells. The stage was now set for even more profound developments in the Mesoproterozoic era, the age of cellular innovation and continental stability. As the Paleoproterozoic gave way to the Mesoproterozoic, the Earth entered a quieter but no less significant chapter in its deep time story. Between 1.6 and 1.0 billion years ago, the surface of the Earth grew more stable. Tectonic activity slowed compared to the upheaval of earlier eras. The skies were beginning to clear, the oceans settled into deeper basins, and the supercontinent known as Nuna or Columbia, formed in the preceding era, entered a period of relative tectonic peace. Though the pace of geological events slowed, evolutionary changes continued to gather momentum. It was a time of deep, slow transformations, an age in which the cell learned to grow, divide, and specialize. The Mesoproterozoic is often referred to as Earth's boring billion years, a nickname that belies the critical innovations that took place during this time. Though there were no sudden mass extinctions, no massive climate disasters, or rapid biological explosions, the evolutionary groundwork laid during this era would eventually make those things possible. It was during this time that the eukaryotic cells, those with nuclei and organelles, began to diversify. These cells, more complex and capable than their prokaryotic ancestors, developed internal compartmentalization that allowed them to perform more sophisticated biological functions. Though life was still microscopic, it had become dramatically more versatile. This cellular complexity led to one of the most important developments in the history of life: sexual reproduction. Prior to this, life reproduced asexually, each organism cloning itself with little variation between generations. Sexual reproduction, however, introduced the mechanism of genetic recombination. It meant variation, adaptability, and a significantly faster evolutionary pace. Though still single-celled, these eukaryotes had begun exchanging genes, reshuffling their DNA with each generation, setting the evolutionary wheels turning toward the rise of multicellular organisms. In the oceans, eukaryotic algae began to thrive, slowly outcompeting some of the simpler cyanobacteria that had dominated the seas for billions of years. These new algal forms came in a variety of shapes and sizes, floating freely or anchoring to shallow seabeds. Some began forming colonies, loose associations of identical cells working in tandem. These colonies, over many generations, would become more integrated, more coordinated, and eventually lay the foundation for true multicellular life. Geologically, the Mesoproterozoic was a time of continental quietude, but not stagnation. The supercontinent of Nuna slowly broke apart and reassembled into a new configuration, Rodinia. This was the first supercontinent in Earth's history for which we have more substantial geological and paleomagnetic evidence. Rodinia was vast and largely lifeless on its surface, but its formation would have had profound effects on ocean circulation, nutrient cycles, and climate. As mountain chains rose and eroded, nutrients such as phosphorus and iron were carried into the oceans, feeding microbial life and driving slow but steady biological productivity. During this time, Earth's atmosphere remained oxygen-rich compared to earlier eras, but far below modern levels. The oxygen produced by photosynthesizing organisms was being used up by reactions with iron and other minerals, and much of it remained dissolved in ocean water rather than accumulating in the atmosphere. Still, it was enough to maintain aerobic respiration, which allowed organisms to extract far more energy from their food than their anaerobic predecessors. This surplus energy supported the development of more complex cellular machinery and, eventually, larger organisms. Sedimentary rocks from this era, particularly in regions like Australia, Canada, and Greenland, preserve striking records of microbial mats, stromatolites, and primitive algae. These fossils, while lacking the drama of trilobites or dinosaurs, offer a quiet but compelling narrative of microbial perseverance and slow evolutionary gain. Stromatolites in particular reached a peak of abundance and diversity during the Mesoproterozoic, covering extensive shallow marine environments. These structures, layer upon layer of sediment trapped by microbial colonies, stand as some of the oldest visible evidence of life still seen in the rock record. Meanwhile, deep beneath the surface, Earth's interior continued its slow churning. The movement of tectonic plates recycled crustal material, forged mountain belts, and occasionally sent superheated plumes of magma to the surface. These processes didn't just shape the continents. They influenced the atmosphere, the oceans, and even life itself. Volcanic eruptions released gases and minerals that fueled oceanic productivity, while tectonic collisions sculpted Earth's topography and helped drive long-term climate patterns. Toward the end of the Mesoproterozoic, some of the earliest true multicellular organisms may have begun to appear, small, soft-bodied algae composed of differentiated cells. Fossils from this era suggest early attempts at organization beyond the single cell. Though still microscopic, these life forms mark the beginning of a biological trend that would later lead to the explosion of complex animal life in the oceans. By the time the Mesoproterozoic era closed, Earth had grown quieter on the surface, but far more dynamic within its oceans and cells. The building blocks for future evolutionary innovation were now firmly in place. Life had evolved from simple to complex cells. Sexual reproduction had begun to shuffle genes and accelerate adaptation, and continents had formed, broken apart, and come together again, bringing new environmental pressures with each rearrangement. The long quiet of the Mesoproterozoic was nearly over. Ahead lay the final era of the Proterozoic Eon, a time of climatic extremes, biological experimentation, and the final tuning of the planet before the arrival of animals. The Neoproterozoic era marked the final chapter of the Proterozoic Eon, a time when Earth began to resemble the planet we know today, not in terms of life on land or the presence of animals, but in its vast geological cycles, climatic extremes, and the dramatic evolutionary shifts that foreshadowed the explosive birth of complex life. Between 1 billion and 541 million years ago, Earth was still a microbial world, but signs of rapid change stirred across the oceans, continents, and atmosphere. The stage was being prepared for a biological revolution, but first, the planet had to endure one of the most severe and mysterious climate events in its history. At the start of the Neoproterozoic, the supercontinent Rodinia held dominance over the globe. It was an immense landmass, its central deserts vast and lifeless, its coastlines battered by warm seas teeming with microbial life. But tectonic forces, slow and relentless, began to tear Rodinia apart. Rifting split continents, forming new ocean basins, and reshaping the map of the world. These tectonic movements not only altered the geography of Earth, but also its climate and the circulation of ocean currents. Over millions of years, the breakup of Rodinia changed weather patterns, eroded vast mountain ranges, and delivered an influx of nutrients into the oceans. It was during this time that the Earth experienced a climatic catastrophe of a scale never seen before or since. A series of global ice ages so severe they may have frozen the planet from pole to equator. Known as the snowball Earth hypothesis, this theory suggests that massive glaciations during the Cryogenian period, a subdivision of the Neoproterozoic, enveloped nearly the entire planet in thick sheets of ice. Glacial evidence has been found on every continent, including regions that were once near the equator, suggesting that ice may have reached tropical zones, leaving only thin slivers of open water near volcanic islands or at equatorial coastlines. The mechanism behind this deep freeze is still debated. Some theories point to the reduction of atmospheric carbon dioxide due to intense weathering and the burial of organic carbon. Others argue that the breakup of Rodinia exposed land at the equator, increasing albedo and reflecting more sunlight back into space. Whatever the cause, the results were catastrophic. Surface temperatures plummeted, oceans froze over, and life was pushed to the brink. For tens of millions of years, Earth remained in this deep freeze, with glaciers grinding across continents and ice covering the seas. And yet, life survived. Microbial communities may have endured in isolated warm pockets, perhaps near hydrothermal vents on the ocean floor, or in thin layers of unfrozen ocean beneath the ice. These environments may have acted as refuges, where evolution quietly continued even as the planet lay silent and frozen above. It's possible that the very stress of these extreme conditions forced life to innovate, pushing the evolution of more resilient, more complex organisms. Indeed, just after the glaciations ended, the fossil record shows a surge in biological experimentation and complexity. Eventually, Earth thawed. The return to a warmer climate may have been triggered by the accumulation of volcanic CO2 in the atmosphere during the deep freeze, eventually creating a runaway greenhouse effect that melted the ice and reignited the global climate system. When the glaciers retreated, they left behind freshly eroded landscapes and nutrient-rich oceans. The sudden release of glacial meltwater and minerals into the seas likely created a nutrient surge, fueling blooms of photosynthetic life and setting off a chain reaction that would transform ecosystems forever. Following the Snowball Earth episodes, during the Ediacaran period, the final subdivision of the Neoproterozoic, life took a bold leap forward. For the first time in Earth's history, multicellular organisms became large enough to be seen with the naked eye. Soft-bodied creatures unlike anything alive today began to appear in shallow marine environments. These strange beings, known as the Ediacaran biota, looked more like abstract art than modern animals. Quilted discs, frond-like stalks, and ribbed ovals that rested on the seafloor. Some may have absorbed nutrients directly from the water, while others may have grazed on microbial mats. These organisms left impressions in sediment that have been preserved as fossils, offering a haunting glimpse into the earliest complex ecosystems. It's still unclear whether these ediacaran organisms were direct ancestors of modern animals or an evolutionary dead end. What's certain is that they represent a critical moment in life's history, an experiment in large-scale multicellularity, in coordinated structure, and in ecological interaction. For the first time, life had not only grown bigger, but also more organized. Cells had begun to specialize, to form tissues and body plans, to sense and respond to the environment in increasingly sophisticated ways. Meanwhile, oxygen levels in the atmosphere continued to rise. The continued proliferation of photosynthetic organisms, especially algae, saturated the oceans and air with oxygen, slowly transforming the environment from one suited only to microbes into one capable of supporting animals with higher energy needs. This oxygenation of the biosphere laid the groundwork for the next great leap, the Cambrian explosion. By the end of the Neoproterozoic, Earth was no longer a microbial planet. It had survived multiple cataclysms, tectonic rifts, snowball glaciations, and mass evolutionary experiments. The continents were shifting into new positions. The oceans teemed with invisible complexity. And in the shallow coastal shelves, soft-bodied life was beginning to stir. The curtain was about to rise on the Phanerozoic Aeon, and with it, the age of animals. Life was ready to explode into diversity, speed, and form. But before that explosion, Earth had already completed one of its greatest transformations, from a planet of rock and water to a world of living, breathing complexity. The Cambrian period marks one of the most profound transformations in the history of life on Earth. After billions of years of evolution, from simple organic molecules to complex single-celled organisms and eventually soft-bodied multicellular life, the Cambrian era burst open with an extraordinary diversification of life forms. Often referred to as the Cambrian explosion, this relatively brief geological interval saw the sudden appearance of most major animal phyla that still exist today. The Earth had been teeming with microbial life for eons, but now, in the span of just a few tens of millions of years, a biosphere of complexity, motion, and interspecies interaction emerged that would shape the trajectory of life forever. At the beginning of the Cambrian, Earth's environment had become increasingly hospitable to life. Oxygen levels had reached a critical threshold, oceans were chemically rich, and shallow marine habitats had expanded along the continental margins. These shallow seas, bathed in sunlight and filled with nutrients from weathering continents, were perfect incubators for biological innovation. Life took advantage of the moment. What had once been a world dominated by microscopic, passive organisms was transformed into an ecosystem full of mobility, predation, armor, eyes, limbs, and competition. It was the dawn of animals in their modern complexity. The Cambrian seas were like alien worlds, filled with bizarre creatures and evolutionary experiments. Trilobites scuttled across the ocean floor, their segmented bodies and compound eyes making them efficient scavengers and foragers. These arthropods were among the most successful animals of the Cambrian, diversifying rapidly into hundreds of species. Alongside them swam predators like Anomalocaris, a strange, torpedo-shaped creature with grasping appendages and a circular mouth lined with serrated plates. It is believed to have been the apex predator of its time, hunting slower and softer prey in a newly competitive marine ecosystem. Among the other strange inhabitants of the Cambrian seas were Hallucigenia, a tiny worm-like creature with spines on its back and legs on its underside, and Opabinia, a soft-bodied animal with 5 eyes and a long, flexible nozzle tipped with a claw. These creatures seem surreal today, but they represent a time of explosive evolutionary experimentation. Many failed branches of the tree of life emerged during this time. Organisms with unique body plans and biological strategies that ultimately went extinct. Yet others would evolve into the ancestors of modern-day arthropods, mollusks, annelids, and chordates. Perhaps most significantly, the Cambrian period saw the emergence of the first chordates, organisms with a notochord, a primitive backbone-like structure. Though simple and small, these early chordates would eventually give rise to vertebrates, fish, amphibians, reptiles, birds, and mammals, including humans. The roots of our own lineage trace back to this revolutionary period. Fossils such as Pikaia, a small, flattened swimming animal found in the Burgess Shale of Canada, offer tantalizing glimpses of what these first chordate organisms may have looked like. The fossil record from the Cambrian is unusually rich due to a key biological innovation, the development of hard parts. Many animals evolved shells, exoskeletons, and other mineralized structures during this period. These provided not only protection from predators, but also greatly enhanced the likelihood of fossilization. The presence of hard parts marked a major shift in evolutionary arms races. Predators adapted to pierce or crush shells, while prey developed more elaborate defenses. This dynamic of predation and defense drove rapid evolutionary changes and ecological complexity. The Cambrian period was also a time of environmental change. Sea levels rose and fell as shallow inland seas expanded across many of the continents. The climate was generally warm, with no evidence of polar ice caps. The oceans were the center of biological activity, as land remained largely barren and lifeless. The chemical composition of seawater was in flux, and changes in oxygen and nutrient availability may have helped drive evolutionary bursts and extinctions within the marine realm. Despite the overall increase in biodiversity, the Cambrian was not without its crises. Shorter extinction events punctuated the period, periodically resetting certain ecosystems and opening niches for new organisms to evolve and expand. These extinctions, while not as catastrophic as the mass extinctions to come in later periods, helped shape the evolutionary trajectory of many animal groups. Toward the end of the Cambrian, some of the early dominant forms began to decline. Many trilobite lineages disappeared, possibly due to environmental shifts or increased competition and predation. New groups were beginning to rise in prominence, setting the stage for even more diversified marine ecosystems in the following period. The basic ecological roles, predator, prey, scavenger, filter feeder, had been established, and the structure of food webs began to resemble something familiar. The Cambrian's legacy is immense. Within a relatively short span of geological time, life transformed from microscopic simplicity into a world of macroscopic variety. Nearly every major group of animals made its first appearance during this period, and many of the ecological and evolutionary rules that govern life today were written in these ancient oceans. It was a time when nature seemed to be experimenting with every possible form and function, and while many of those early forms vanished, their legacy lived on in the successful lineages that followed. As the Cambrian period came to a close around 485 million years ago, Earth's biosphere had become irreversibly complex. The oceans pulsed with life, predators hunted with purpose, and organisms moved with intent across layered seafloors. With this new vitality and structure in place, life was prepared to explore even more diversity, to build reef systems, to colonize new marine zones, and eventually, to make the leap onto land. The next era, the Ordovician, would take the complexity of life even further. The Ordovician period ushered in a new wave of biological complexity, building upon the innovations of the Cambrian and extending life's reach into new ecological frontiers. Spanning roughly 41 million years, this period witnessed a dramatic expansion of marine biodiversity, the first appearance of vertebrates with mineralized skeletons, the formation of the earliest coral reefs, and significant shifts in the configuration of continents and ocean systems. It was a time of ecological flourishing followed by one of Earth's first great extinction events, a pattern of growth and collapse that would become familiar in the planet's biological history. At the dawn of the Ordovician, life was still confined to the oceans. The land remained barren, dominated by windswept rock, sand, and volcanic plains, with no vegetation or animals in sight. But beneath the waves, life teemed in extraordinary abundance and variety. The warm, shallow seas that covered much of the planet provided ideal conditions for marine organisms to thrive and diversify. Trilobites, which had flourished during the Cambrian, continued to evolve into new forms, while brachiopods, shellfish resembling modern clams, became highly abundant and widespread. Mollusks, particularly the cone-shaped nautiloids, grew larger and more active, some reaching several meters in length, becoming the top predators of their ecosystems. One of the most significant developments of the Ordovician was the rise of the first coral reefs. Built by early tabulate and rugose corals, as well as by stromatoporoids, these reef systems provided complex habitats for other marine life. Reefs supported a wide range of filter feeders, scavengers, and predators, promoting the diversification of ecological roles. This structuring of the marine environment into layered, three-dimensional spaces allowed for the emergence of new niches and accelerated evolutionary experimentation. The period also saw the appearance and radiation of the first jawless fish, known as agnathans. These primitive vertebrates were small and armored with bony plates, feeding on particles and detritus from the seafloor. Though modest in appearance, they represented a crucial evolutionary step toward the vertebrate body plan that would later dominate both water and land ecosystems. Their skeletons were still cartilaginous, but their external armor hinted at the later development of internal bone and jaws. Another major Ordovician innovation was the rise of planktonic life. Tiny, drifting organisms such as graptolites became especially abundant. Graptolites were colonial animals that floated freely in the ocean, feeding on microscopic plankton. Their widespread presence and rapid evolution make them excellent index fossils, helping geologists to precisely date Ordovician rock layers. Phytoplankton also diversified, playing an increasingly important role in oceanic food chains and contributing to atmospheric oxygen levels. Tectonically, the Ordovician world was dynamic. The supercontinent Gondwana drifted southward, approaching the South Pole, while other land masses, such as Laurentia, modern-day North America, Baltica, and Avalonia, moved toward the equator. These shifting land masses influenced ocean currents and climate patterns, which in turn shaped evolutionary pressures. Sea levels were generally high, with vast shallow seas covering continental interiors, but by the end of the period, dramatic changes began to unfold. Around 447 million years ago, the planet entered into one of its earliest known ice ages. Glaciers began to form on Gondwana, which had now drifted over the South Pole. As ice sheets grew, sea levels dropped dramatically, draining the shallow marine habitats that had nurtured so much of Ordovician life. The cooling climate and shrinking habitats created a cascade of environmental stresses that many organisms could not survive. This climatic upheaval triggered what is now recognized as the Ordovician-Silurian extinction event, the second largest mass extinction in Earth's history. It is estimated that around 85% of marine species went extinct, including many trilobites, brachiopods, graptolites, and reef-building organisms. The extinction unfolded in two major pulses, the first driven by cooling and falling sea levels, and the second by subsequent warming and anoxic, low oxygen, conditions in the oceans as glaciers melted and seas returned. Despite the devastation, this extinction event paved the way for new evolutionary opportunities in the following Silurian period. The survivors of the Ordovician bottleneck would go on to diversify into new forms and colonize previously unoccupied ecological niches. In a sense, the crisis reset the biological landscape, allowing new innovations and lineages to emerge. The Ordovician was a period of both triumph and tragedy, of stunning biological radiation followed by catastrophic collapse. It expanded the boundaries of marine life, introduced new forms of mobility, feeding, and habitat construction, and saw the rise of the earliest vertebrates and reef systems. It was also a sobering reminder of Earth's capacity for rapid environmental change and the fragility of even the most successful ecosystems. By the end of the Ordovician, the Earth had changed dramatically. Its climate had shifted, its oceans had drained and refilled, and its biosphere had been reshaped by the pressure of extinction. Yet life, as it always does, endured and adapted. The planet was entering a new phase, where life would rebound with renewed energy and where the first tentative steps toward land colonization would soon begin. The Silurian period was about to begin, and with it, the next chapter in Earth's unfolding biological drama. The Silurian period, following the massive Ordovician-Silurian extinction event, was a time of recovery, resilience, and quiet revolution. Though it lacked the explosive diversification of the Cambrian or the grand climatic upheavals of the Ordovician, the Silurian marked an important transition in Earth's biological and geological narrative. Life rebounded after the devastation, new ecosystems emerged, and perhaps most significantly, the first pioneering steps were taken from sea to land. The Silurian was a bridge between worlds, a time when Earth's biosphere, once entirely aquatic, began to reach upward and outward toward dry ground. In the wake of the Ordovician extinction, Earth's shallow seas once again became fertile grounds for evolutionary experimentation. The climate gradually stabilized, warming after the brief but intense ice age. Glaciers retreated from the supercontinent Gondwana, sea levels rose, and flooded continental shelves once more provided rich, sunlit habitats for marine life. Though the diversity of species was reduced at the beginning of the period, evolutionary recovery proceeded quickly. Marine communities began to repopulate, and by the middle of the Silurian, ecosystems were flourishing again. Coral reefs, devastated during the extinction, began to rebuild. New forms of tabulate and rugose corals re-established reef systems, which became centers of biodiversity. Brachiopods, crinoids, bryozoans, and mollusks all diversified within these reef environments, creating complex marine food webs. Trilobites, though past their peak, remained common, while eurypterids, often called sea scorpions, emerged as significant predators. Some of these eurypterids reached impressive sizes, over 2 meters in length, and occupied both marine and brackish water environments, hinting at their adaptability and evolutionary potential. The vertebrate lineage also advanced. Jawless fish, agnathans, continued to evolve, their bony head shields becoming more elaborate, offering better protection and structural support. More importantly, the Silurian witnessed the first appearance of jawed fish, the placoderms, and early acanthodians. The development of jaws was a monumental evolutionary step. It opened up entirely new feeding strategies, predation, grasping, tearing, and allowed vertebrates to move beyond filter feeding and scavenging. With jaws came mobility, power, and competitive advantage, setting the stage for the rise of fish as dominant marine animals in the periods to come. But perhaps the most transformative development of the Silurian took place not in the seas, but on land. For billions of years, the continents had remained lifeless, bare rock subjected to erosion, wind, and volcanic activity. But during the Silurian, microscopic life began to establish itself in moist environments along the coasts and riverbanks. Algae and fungi colonized wet soil surfaces, forming symbiotic relationships that helped stabilize sediments and initiate the formation of the first primitive soils. From these early communities, the first land plants evolved. The earliest terrestrial plants were small and simple, non-vascular, lacking true roots, leaves, or stems, but they marked a critical step in Earth's history. Fossils of Cooksonia, one of the earliest known land plants, show a tiny, branching stalk with spore-producing structures at the tips. These plants were only a few centimeters tall, but their arrival on land had vast implications. They began to influence atmospheric carbon dioxide levels, contribute to soil development, and create habitats that could eventually support terrestrial animals. The transition to land was slow and fraught with challenges. Life had evolved in water, where buoyancy supported soft bodies, where reproduction depended on moisture, and where nutrients were easily absorbed. On land, organisms had to contend with gravity, desiccation, and ultraviolet radiation. But evolution is patient. The Silurian laid the groundwork for adaptations that would one day make complex terrestrial ecosystems possible. Arthropods, which had been enormously successful in the oceans, were among the first animals to venture onto land. Fossil evidence suggests that millipede-like creatures may have appeared on land during the Silurian, possibly feeding on decaying plant matter or microbial mats. These early pioneers would eventually give rise to the vast diversity of terrestrial arthropods, spiders, insects, scorpions, that would dominate land ecosystems for hundreds of millions of years. Geologically, the Silurian continued the tectonic rearrangements of earlier periods. Laurentia, Baltica, and Avalonia moved closer together, eventually colliding to form a new landmass known as Euramerica, or the Old Red Sandstone Continent. These collisions created mountain ranges and influenced ocean circulation patterns, further shaping climate and evolutionary pressures. The climate during the Silurian was generally warm and stable, especially in contrast to the glacial extremes of the late Ordovician. Polar regions were relatively ice-free, and the warm, shallow seas allowed for widespread carbonate deposition, forming limestone beds rich in marine fossils. These favorable conditions helped sustain the recovery and diversification of life across the globe. By the end of the Silurian, Earth was no longer just a world of oceans and microbial mats. Plants had begun to green the edges of continents. Arthropods were testing the possibilities of terrestrial life, and fish with jaws were beginning to assert their dominance in aquatic food chains. Evolution was preparing for a new wave of innovation, one that would take the small, humble steps of the Silurian and amplify them into the towering forests, colossal predators, and complex ecosystems of the Devonian. The Silurian period may not be as well known as others, but it was a pivotal moment in Earth's history, a time of quiet reconstruction, cautious expansion, and subtle revolution. It set the stage for one of the most dramatic and dynamic periods in the planet's biological story, where life would not only evolve further, but take a bold leap into a new world, the land. The Devonian period is often called the Age of Fishes, and for good reason. During these 60 million years, fish diversified into an incredible array of forms, sizes, and lifestyles, laying the foundation for all future vertebrate life. But the Devonian was more than a golden era for aquatic creatures. It was also the time when life made its first real conquest of land in earnest. Plants spread across the continents, forming the first forests. Arthropods followed, and eventually, vertebrates, our distant ancestors, began the monumental transition from water to land. This was a period of bold evolutionary experiments, of vast biological expansion, and of new ecosystems rising from previously lifeless ground. At the beginning of the Devonian, Earth's continents were still shifting. Gondwana dominated the southern hemisphere, while the smaller land masses of Laurentia, Baltica, and Avalonia had joined to form Euramerica. This new supercontinent straddled the equator and was mostly covered in warm, tropical seas. These shallow marine environments provided the perfect breeding grounds for evolutionary innovation. Coral reefs, more extensive than ever before, flourished with biodiversity. Stromatoporoids and tabulate corals built massive reef complexes, supporting an abundance of marine life from tiny filter feeders to large predators. The fish of the Devonian were unlike anything the Earth had seen. Placoderms, armored fish with bony plates covering their heads and thoraxes, were dominant in the early Devonian seas. Among them was Dunkleosteus, a fearsome apex predator that could grow over 6 meters long, with a bite force capable of crushing bone. Placoderms were some of the earliest jawed vertebrates, and their success demonstrated the power and versatility of jaws in evolutionary terms. Alongside them swam the cartilaginous ancestors of modern sharks, as well as the early bony fish that would eventually evolve into all ray-finned and lobe-finned fish. It was within the lobe-finned fish that one of the most important evolutionary transitions took place. These fish had paired, fleshy fins supported by bone structures that resembled the limb bones of tetrapods. Over millions of years, some of these fish began to adapt to life in shallow, swampy environments. Their fins became stronger and more limb-like. Their lungs, originally evolved as a secondary breathing structure in oxygen-poor water, grew more efficient. Eventually, these lobe-finned fish gave rise to the first tetrapods, four-limbed vertebrates capable of venturing onto land. This transition did not happen overnight, nor did it result in fully terrestrial animals right away, but it marked the beginning of one of the most significant evolutionary narratives in Earth's history. While vertebrates were taking their first steps onto land, plants were advancing in a different, but equally groundbreaking way. The first land plants had appeared during the Silurian, but in the Devonian they exploded in diversity and size. Vascular plants, those with specialized tissues for transporting water and nutrients, spread rapidly. They developed roots, leaves, and woody stems, which allowed them to grow taller and colonize a variety of terrestrial environments. Primitive forests began to form, with early trees such as Archaeopteris reaching heights of 10 to 30 meters. These forests were transformative. They stabilized soils, created new habitats, and altered the global climate by drawing down atmospheric carbon dioxide and contributing to long-term cooling. As plant life spread across the continents, it created new opportunities for animal colonization. Arthropods, including centipedes, millipedes, and early insects, followed the greenery onto land, evolving to exploit these new food sources and environments. Some of the first complex food webs began to form outside of water, though terrestrial ecosystems remained relatively simple compared to the oceans. Amphibious tetrapods, descendants of lobe-finned fish, began to populate freshwater margins and swampy areas, relying on both gills and primitive lungs for breathing. These early vertebrates were limited in mobility and tied closely to moist environments, but they represented the beginning of a slow but steady conquest of the terrestrial realm. Despite the vast progress of life, the Devonian was not without disruption. The end of the period was marked by a series of extinction events, sometimes collectively called the Late Devonian Extinction. Unlike the sudden, catastrophic events of other periods, the Devonian extinctions were drawn out and complex, unfolding over several million years. Reef systems collapsed, and marine biodiversity declined significantly. Trilobites, brachiopods, and many species of fish suffered heavy losses. The causes are still debated, but likely involved a combination of climate change, ocean anoxia, lack of oxygen, rising and falling sea levels, and possibly even volcanic activity or asteroid impacts. These extinctions were selective. While many shallow marine species were wiped out, life in deeper waters and on land fared better. The devastation in the oceans may have opened up ecological space for new evolutionary developments in the following periods. On land, forests continued to expand, and the vertebrate lineage that would eventually lead to reptiles, birds, and mammals survived and slowly diversified. The Devonian was thus a paradoxical time. On one hand, a period of vibrant growth and innovation. On the other, a time of looming crisis and mass extinction. In the larger story of Earth's history, the Devonian represents a moment when life changed its strategy. No longer confined to water, organisms now began shaping the very landscapes around them. Roots cracked rocks and built soil. Trees pulled moisture and carbon from the air. Animals explored new dimensions of existence, breaking free from the buoyancy of water to brave the unyielding gravity of land. It was a time of pioneering and persistence, of breakthroughs that would echo through every era that followed. The Carboniferous period was a time of extraordinary transformation, one that brought Earth closer to the world we know today. It was a period of dense, lush vegetation, towering forests, and oxygen-rich air. It was also a time of giant insects, amphibians exploring the land in greater numbers, and the first appearance of reptiles, the earliest truly terrestrial vertebrates. Named for the vast coal deposits that formed from its ancient forests, the Carboniferous was a green and humid world where the foundation for modern terrestrial ecosystems was laid. For 60 million years, Earth was wrapped in a cloak of green, its continents breathing, decaying, and slowly forming the fossil fuels that would shape the destiny of future civilizations. At the beginning of the Carboniferous, the planet's geography was in flux. The supercontinent Gondwana continued drifting across the southern hemisphere, while smaller land masses such as Laurussia and Siberia moved toward eventual collision. These tectonic shifts created vast mountain ranges and influenced global climate and sea levels. Much of the planet's surface was covered in warm, shallow seas, while equatorial regions hosted immense, swampy rainforests fed by high humidity and heavy rainfall. These equatorial forests stretched across what are now Europe, North America, and parts of Asia, regions that would one day become the great coal belts of the industrial age. The lush vegetation of the Carboniferous forests was dominated by giant lycopods, horsetails, and ferns, plants that towered tens of meters into the air. Lepidodendron, one of the most prominent trees of the time, could grow over 30 meters tall, with a scaly bark and crown of leaves that spread like an umbrella. These were vascular plants, but they reproduced using spores rather than seeds, which meant they still required moist environments for their life cycles. In the shadow of these ancient giants grew a dense understory of seed ferns and early conifers, while thick mats of moss and algae blanketed the forest floor. The sheer volume of plant life during the Carboniferous contributed to a unique atmospheric condition. Through photosynthesis, these plants pumped vast amounts of oxygen into the air, pushing atmospheric oxygen levels to unprecedented heights, possibly as high as 35%, compared to today's 21%. This elevated oxygen concentration had profound effects on life. Arthropods, especially insects, were able to grow to enormous sizes. Giant dragonflies like Meganeura, with wingspans of over 70 centimeters, soared above the treetops. Millipedes and scorpions reached lengths of over a meter. These oversized creatures thrived in the oxygen-rich, humid air and dense foliage of the Carboniferous world. Vertebrate life was also undergoing dramatic evolution. Amphibians, which had first appeared in the Devonian, diversified and radiated into a wide range of ecological roles. They came in many forms and sizes, from small, lizard-like insectivores to large, crocodile-sized predators. These early tetrapods were still largely tied to water for reproduction, but their increasingly strong limbs, lungs, and sensory systems allowed them to exploit terrestrial environments more effectively than ever before. One of the most pivotal developments of the Carboniferous was the evolution of the amniotic egg. This innovation allowed vertebrates to reproduce without returning to water, as the egg contained all the nutrients and protective membranes needed to support an embryo on land. This breakthrough led to the rise of the first reptiles, creatures that could truly call the land their permanent home. These early reptiles were small and agile, well suited to the drier niches at the edges of the vast swamp forests. From this humble beginning, the reptilian lineage would go on to produce dinosaurs, birds, and ultimately mammals. The climate of the Carboniferous remained warm and humid for much of the period, supporting the proliferation of vast coal-forming forests. However, near the end of the Carboniferous, a significant climatic shift began. As Gondwana moved over the South Pole, massive ice sheets formed, triggering the onset of a global ice age. This glaciation, known as the Late Paleozoic Ice Age, caused sea levels to fall and dramatically altered ecosystems. The cooling and drying climate led to the collapse of the swamp forests in many regions, particularly in Euramerica, and ushered in the transition to more arid conditions in the following Permian period. Despite the climatic upheaval, the legacy of the Carboniferous would endure. The organic material buried in its swamps, trunks, leaves, spores, and roots was compacted and transformed over millions of years into coal. These coal seams, formed during the high-productivity forests of the Carboniferous, would become the fuel of human industry hundreds of millions of years later, powering the machines of the Industrial Revolution and transforming human society. The Carboniferous was a paradoxical period, one of abundance and excess, but also of transition and fragility. It brought oxygen-rich skies, towering forests, and giant life forms, while also setting the stage for climatic challenges and evolutionary refinement. It was a green world in every sense, vibrant, growing, and alive, but it was also a world that was learning to adapt to new pressures, new climates, and new forms of life. From the thick mists of ancient swamps, the Earth was slowly evolving into something more complex, more diverse, and more prepared for the challenges of the future. The Permian period marked the grand finale of the Paleozoic era, a time of extremes, innovation, and ultimately, profound catastrophe. Over nearly 50 million years, the Earth saw the rise of new ecosystems, dramatic climatic changes, and the formation of the supercontinent Pangaea. It was a time of evolution pushed to its limits, where reptiles rose to dominance. Mammal-like ancestors began their journey toward true mammals, and vast deserts replaced the once lush Carboniferous swamps. But the Permian's most defining feature would be its end, the greatest mass extinction in Earth's history, an event so devastating that it nearly wiped the slate clean. At the dawn of the Permian, the Earth was in the midst of massive tectonic upheaval. The continents had drifted together to form a single colossal landmass, Pangaea, which stretched nearly from pole to pole. This new configuration had enormous impacts on global climate and ocean circulation. Much of the interior of Pangaea was arid and prone to temperature extremes, lacking the moderating influence of large bodies of water. The vast coastal areas, meanwhile, were bordered by the Panthalassic Ocean and the shrinking remnants of the Paleotethys Sea. These shifting environments would drive evolutionary pressures in new and often unforgiving directions. The tropical swamp forests of the Carboniferous had largely vanished by the early Permian, replaced by more drought-tolerant vegetation such as conifers, seed ferns, and ginkgos. These plants were better suited to the drier, more seasonal climates of the Permian world, and they would become dominant components of many terrestrial ecosystems. The diversification of gymnosperms, seed-producing plants that did not require water for reproduction, was a crucial adaptation to the increasingly dry conditions and allowed plant life to colonize upland and inland areas more successfully than ever before. The animal life of the Permian reflected this transition. Amphibians, once dominant, began to decline in diversity and range, as their need for moist environments limited their ability to compete in drier climates. In their place rose a new class of vertebrates, amniotes, creatures that laid eggs with protective membranes, allowing them to fully escape aquatic reproduction. These animals split into two major lineages: the sauropsids, the ancestors of reptiles and birds, and the synapsids, the ancestors of mammals. Among the synapsids, a wide array of forms evolved during the Permian, from the sailback Dimetrodon, often mistaken for a dinosaur, to more advanced therapsids, which began to exhibit mammalian characteristics. These included differentiated teeth, upright limb posture, and possibly even fur or hair in some species. Therapsids became the dominant terrestrial vertebrates of the mid to late Permian, filling roles from predators to herbivores in complex land ecosystems. They were agile, adaptable, and increasingly efficient in regulating their body temperatures, a key step on the long path toward true endothermy. Reptiles, too, were diversifying, with early forms adapting to a range of ecological roles. Some, like the pariasaurs, were large, armored herbivores, while others remained small and insectivorous. These reptiles would go on to give rise to the archosaurs, the group that would eventually include dinosaurs, pterosaurs, and crocodilians in the following Mesozoic era. Marine life in the Permian was also rich and varied. Coral reefs, sponges, brachiopods, mollusks, and echinoderms continued to thrive in warm, shallow seas. Ammonoids and nautiloids were common, and new predatory fish evolved to exploit a wide range of niches. For most of the Permian, marine ecosystems were stable and productive, with complex food webs supporting both invertebrates and vertebrates. However, toward the end of the period, this stability would unravel. The end Permian extinction, also known as the Great Dying, was the most catastrophic biological event in Earth's history. Occurring around 252 million years ago, it wiped out an estimated 90 to 96% of all marine species and about 70% of terrestrial vertebrates. Entire ecosystems collapsed. Coral reefs disappeared. Forests were obliterated. It took life on Earth millions of years to recover. The causes of this extinction are still debated, but the leading hypothesis involves massive volcanic activity in what is now Siberia. These eruptions, known as the Siberian traps, released colossal amounts of carbon dioxide and other gases into the atmosphere, triggering runaway global warming, ocean acidification, and anoxia, conditions in which the oceans lose their oxygen. The combination of heat, acid, and stagnation in the seas led to the death of plankton, the collapse of marine food chains, and the suffocation of nearly every ocean ecosystem. On land, extreme warming, drought, and habitat destruction led to widespread extinctions and the disappearance of entire evolutionary lineages. The Permian extinction was not a single, instantaneous event, but a prolonged crisis that unfolded over hundreds of thousands of years. It was an ecological tipping point, beyond which many forms of life could not adapt quickly enough. Yet, from this devastation, a new chapter in life's history would begin. The survivors of the Permian extinction, scattered, reduced, and reeling, would become the progenitors of the Mesozoic world. Reptiles, once marginal, would rise to new dominance. The early synapsids that endured would eventually give rise to mammals. In this way, the Permian, though a period of incredible loss, was also a moment of clearing, a painful reset that would allow the evolutionary experiments of the next era to flourish. The Permian period was a world in transition, both geographically and biologically. It was a time of adaptation, resilience, and the slow march toward complexity. But it was also a reminder of life's fragility, of how even the most stable-seeming ecosystems can fall to forces beyond their control. The world would never be the same after the Permian, but the life that emerged from its ashes would go on to create some of the most spectacular creatures the planet has ever seen. The Triassic period stands as a stark contrast to the chaotic end of the Permian, a chapter where life began to rebuild from the brink of annihilation. In the wake of the Great Dying, Earth was a quiet, desolate world. Oceans were nearly empty, forests were sparse or absent, and evolutionary possibilities hung in the balance. It took millions of years for ecosystems to recover, and during that slow resurgence, entirely new forms of life began to rise. The Triassic was a crucible for the future, an experimental period in which many of the dominant creatures of the Mesozoic, most notably the dinosaurs, first took shape. In the space of about 50 million years, life transformed from near oblivion into a thriving, diverse, and increasingly complex biosphere. At the outset of the Triassic, the planet's land masses were still unified in the vast supercontinent of Pangaea. This massive landmass stretched from pole to pole, surrounded by a single global ocean called Panthalassa. The arrangement had profound effects on climate and ecology. Much of the interior of Pangaea was dry and desert-like, far from the moderating influence of the sea. Rainfall was limited and seasonal, temperatures fluctuated widely, and weather patterns were harsh and unpredictable. Coastal regions and areas near inland seas were more hospitable, but overall, the climate was extreme and demanding. In these austere conditions, life found footholds where it could. The first 10 million years or so of the Triassic were marked by low biodiversity and ecosystems dominated by generalist survivors of the Permian extinction. In the oceans, species diversity was a fraction of what it had been. Coral reefs had vanished, and recovery was slow. Brachiopods, mollusks, ammonoids, and marine reptiles began to re-establish ecological roles. Notably, the Triassic saw the rise of ichthyosaurs, dolphin-shaped marine reptiles adapted for fast swimming and hunting, and later, the appearance of plesiosaurs, with their long necks and paddle-like limbs. These animals would come to dominate Mesozoic seas. On land, flora began to repopulate the surface. Gymnosperms, such as cycads, conifers, and ginkgos, spread across the dry landscapes, their seeds and vascular systems well suited for arid conditions. Grasses and flowering plants had not yet evolved, so the Triassic world was a realm of spiky, thick-leaved trees and shrubs that tolerated the sun and survived with minimal water. By the mid-Triassic, the first true dinosaurs appeared. They were small, lightly built, and likely fast-moving. Far from the titanic giants of the Jurassic and Cretaceous, these early dinosaurs were opportunistic survivors in a competitive world. What set them apart was their posture, the erect, pillar-like limbs that gave them efficient movement, and their lungs and metabolism, which may have allowed for sustained activity. Over the next tens of millions of years, these modest beginnings would lead to one of the most successful and iconic groups of animals in Earth's history. Alongside the dinosaurs, pterosaurs also took flight in the late Triassic. These were the first vertebrates to achieve powered flight, predating birds by over 70 million years. Their wings, formed by a membrane stretched across an elongated fourth finger, were a unique evolutionary innovation. Pterosaurs ranged from sparrow-sized flyers to larger gliders, and though they were not yet dominant, their appearance marked another breakthrough in vertebrate evolution. As ecosystems recovered, new niches formed and biodiversity increased steadily. Herbivorous reptiles like Plateosaurus, a large, bipedal sauropodomorph, roamed open plains, feeding on conifers and ferns. Carnivorous archosaurs hunted in packs or alone, filling roles that had once been occupied by synapsids. The Triassic was a time of replacement, of old dynasties giving way to new ones. But just as the planet had begun to stabilize, another mass extinction arrived at the end of the Triassic. Though not as devastating as the Permian event, the Triassic-Jurassic extinction eliminated around 70 to 75% of all species. The causes are still debated, but likely involved massive volcanic activity in the Central Atlantic Magmatic Province, which released vast amounts of carbon dioxide and other gases into the atmosphere. Global warming, acidification of the oceans, and ecosystem collapse followed, selectively removing many of the large amphibians, early reptiles, and marine groups. In the aftermath of this extinction, the evolutionary playing field was reset once again. But this time, the survivors included dinosaurs, pterosaurs, and the ancestors of crocodiles and mammals. The extinction cleared the way for these groups to dominate the Jurassic and beyond. The Triassic period was a time of recovery, experimentation, and ultimately, transition. Life clawed its way back from the dead, reassembled itself into new forms, and laid the foundations for some of the most magnificent creatures to ever walk, swim, or fly across the earth. From humble beginnings, the age of dinosaurs was now poised to take center stage, and with it, the Mesozoic world would reach its full, thunderous potential. The Jurassic period is perhaps the most iconic slice of Earth's history, immortalized in films, museums, and imaginations across the world. Spanning 56 million years, it was a time of expansion, flourishing biodiversity, and continental rearrangement. In this chapter of deep time, dinosaurs rose to true global dominance. The first birds took to the skies, and Earth's landscapes were lush, warm, and alive with sound and movement. The world of the Jurassic was profoundly different from both the desolate Triassic that preceded it and the colder, more fragmented modern Earth that followed. It was a greenhouse world, humid, verdant, and teeming with evolutionary innovation. At the beginning of the Jurassic, Earth was still recovering from the Triassic-Jurassic extinction event. That mass extinction had cleared away many of the large amphibians and early reptilian competitors, opening ecological space for dinosaurs to radiate into new forms and habitats. As a result, the Jurassic saw the explosive diversification of these remarkable creatures, who came to occupy every major terrestrial niche. Herbivores and carnivores, bipedal runners and quadrupedal giants, armored forms and long-necked grazers. Geographically, the supercontinent Pangaea had begun to rift apart, slowly dividing into the northern continent Laurasia and the southern landmass Gondwana. This tectonic activity created new coastlines, shallow seas, and inland basins that fostered increased regional diversity. Oceans like the Tethys Sea began to expand, while massive volcanic activity and the movement of land masses contributed to a warm, humid, and relatively stable global climate. Polar ice was absent, and dense vegetation covered much of the planet. Flora during the Jurassic was dominated by gymnosperms, particularly conifers, cycads, and ginkgos. Ferns and horsetails thrived in the understory, and mosses carpeted the ground. Grasses and flowering plants had not yet evolved, so these forests were structurally and visually different from the ones we know today. Nonetheless, they provided a rich and stable food base for the growing population of herbivorous dinosaurs. Among the herbivores, the sauropods emerged as the undisputed giants of the Jurassic. Dinosaurs like Brachiosaurus, Diplodocus, and Apatosaurus reached sizes never before seen on land, with necks that stretched to treetops and tails that acted as counterbalances or even whips. These colossal animals moved slowly but surely across floodplains and forests, likely in herds, their massive size offering protection from predators. Their physiology remains a topic of fascination. How they breathed, digested, and moved such enormous bodies is still being explored today. To feed on such immense creatures, predators had to adapt. Enter the theropods, bipedal, often fast-moving carnivores that varied widely in size and specialization. Allosaurus was one of the top predators of the late Jurassic, a formidable hunter with powerful jaws and serrated teeth. Smaller theropods, such as Ornitholestes and Coelophysis, hunted smaller prey or scavenged, and some showed signs of complex social behavior or pack hunting. Feathers, long thought exclusive to birds, likely appeared among some of these theropods during the Jurassic, suggesting a link between thermoregulation, display, and eventual flight. Indeed, one of the most groundbreaking events of the Jurassic was the evolution of birds from small feathered theropods. The most famous transitional fossil, Archaeopteryx, lived around 150 million years ago and bore both reptilian and avian traits: teeth, a bony tail, clawed fingers, but also flight feathers and a wishbone. Archaeopteryx marks a critical moment in evolutionary history, the bridging of reptiles and birds, the moment when dinosaurs began to take to the skies not as gliders, but as powered flyers. Marine life also flourished during the Jurassic. Shallow seas spread across many parts of the continents, providing ideal conditions for reefs, invertebrates, and marine reptiles. Ammonites were abundant, their coiled shells drifting in currents and serving as key components of the marine food web. Ichthyosaurs remained successful, resembling modern dolphins in form and movement, while plesiosaurs with long necks and turtle-like bodies hunted fish and cephalopods. Pliosaurs, shorter-necked but more powerfully built, acted as apex predators of the seas. In the skies, alongside early birds, the pterosaurs expanded into a wide variety of forms. From the small, sparrow-sized Anurognathus to larger species with wingspans stretching several meters, pterosaurs became increasingly specialized in flight. Their lightweight skeletons, membranous wings, and advanced flight muscles allowed them to dominate aerial ecosystems long before birds became widespread. Back on land, the diversity of ecosystems continued to expand. Floodplains, river deltas, coastal lagoons, and dense forests all supported complex webs of life. Insects such as beetles, dragonflies, and early butterflies buzzed through the undergrowth, pollinating or feeding on plants. Mammals, although still small and relatively rare, were present throughout the Jurassic. These early mammals, descended from the surviving synapsids of the Triassic, were typically nocturnal, insectivorous, and highly adaptable. Their small size likely helped them avoid predation and competition with the dominant dinosaurs, allowing them to quietly persist and diversify in the shadows. The Jurassic was not just a period of biological flourishing, it was also a time of increasing ecological sophistication. Food webs became more intricate, interspecies interactions more dynamic. Species began to specialize in new ways, giving rise to unique behaviors and morphologies. Evolution operated at full speed, and life on Earth became more intricate, layered, and resilient. As the Jurassic drew to a close, tectonic forces continued reshaping the continents, and sea levels remained high. Volcanic activity persisted, but no major extinction event marked the end of the period. Instead, the Jurassic transitioned relatively smoothly into the Cretaceous, setting the stage for further evolution, the spread of flowering plants, and the ultimate climax of the age of dinosaurs. The Jurassic period, then, was a golden age of giants, a time when the Earth was warm and wet, when the skies were alive with wings, and the land shook with the footsteps of titans. It was the era that cemented dinosaurs as the dominant terrestrial animals and laid the foundation for modern birds and mammals. It was, in many ways, nature's grand rehearsal before its most spectacular performance yet. The Cretaceous period marks the final and perhaps most dynamic chapter in the Mesozoic era, a time when life on Earth reached new heights of diversity, complexity, and global distribution. Lasting for nearly 80 million years, the Cretaceous was the longest period in the Phanerozoic Eon and witnessed some of the most profound evolutionary and geological transformations in Earth's history. It was during this time that dinosaurs reached their apex. Flowering plants revolutionized terrestrial ecosystems, and the continents took on a form that more closely resembles their present configuration. Yet, despite all this progress, the Cretaceous would end not with a gradual transition, but with a sudden, world-shattering extinction event that would permanently alter the course of life on Earth. Geologically, the Cretaceous was a period of intense tectonic activity. The supercontinents continued to break apart. Laurasia in the north and Gondwana in the south fractured into the continents we know today. This breakup widened the Atlantic Ocean, reshaped coastlines, and created numerous shallow inland seas. In North America, the western interior seaway split the continent in half, creating a warm, tropical marine corridor teeming with life. The movement of plates also triggered extensive volcanic activity and mountain building, most notably the early stages of the formation of the Rocky Mountains. The climate of the Cretaceous was generally warm and stable, with little or no polar ice. Sea levels were high, submerging large areas of the continents under shallow seas. These warm, nutrient-rich waters supported vast plankton blooms and coral reefs, forming the basis of robust marine food webs. Ocean circulation patterns were different from today due to the arrangement of land masses, and oxygen levels may have fluctuated in some deep marine environments, causing periodic anoxic events that affected marine life. In the oceans, marine reptiles such as mosasaurs, enormous, serpentine predators, rose to prominence, replacing the declining ichthyosaurs. Plesiosaurs and pliosaurs remained formidable hunters, while ammonites and belemnites continued to flourish as common cephalopods. Fish evolved into more modern forms, including early representatives of teleosts, which today dominate oceanic ecosystems. Sea turtles, marine crocodiles, and large predatory sharks also swam the Cretaceous seas, creating a layered and competitive aquatic environment. On land, the Cretaceous was the peak of dinosaur diversity. Herbivores evolved into an astonishing variety of forms. The long-necked titanosaur sauropods roamed southern continents. Hadrosaurs, or duck-billed dinosaurs, became the most numerous herbivores in many ecosystems, and ceratopsians, like Triceratops, emerged with their distinctive horns and frills, possibly used for display, defense, or social interaction. Ankylosaurs developed heavy armor and tail clubs, while pachycephalosaurs sported dome-shaped skulls, potentially used for headbutting contests or species recognition. Carnivorous dinosaurs also reached new evolutionary heights. Tyrannosaurs became apex predators in the northern hemisphere, with Tyrannosaurus rex representing the culmination of their lineage, immensely powerful, keenly aware, and devastatingly efficient. In the southern continents, other giant theropods such as Giganotosaurus and Carnotaurus filled similar ecological roles. Raptors, including members of the dromaeosaurid family, became more refined, exhibiting bird-like characteristics such as feathers, advanced vision, and possibly pack hunting behavior. But perhaps the most revolutionary development of the Cretaceous was the rise of angiosperms, flowering plants. These plants, which reproduce using enclosed seeds and often rely on animal pollination, dramatically changed terrestrial ecosystems. Flowers allowed for more precise fertilization, faster reproduction cycles, and coevolution with pollinators like insects. Bees, butterflies, and other pollinating insects appeared and diversified rapidly in response, triggering a cascade of ecological interdependencies. Forests became more colorful, varied, and structurally complex, and herbivorous dinosaurs adapted to browsing these new types of foliage. Alongside this botanical revolution, the first true grasses also began to evolve, although they wouldn't become widespread until much later. These innovations in plant life helped sustain large populations of herbivores and, by extension, their predators. The ecosystems of the Cretaceous were increasingly dynamic, with rich food chains, specialized behaviors, and growing complexity. Avian dinosaurs, true birds, continued to evolve from small feathered theropods, becoming more diverse and better adapted to flight. Some developed toothless beaks and other modern bird traits, while others still retained claws or teeth. The skies were also dominated by advanced pterosaurs such as Quetzalcoatlus, with wingspans exceeding 10 meters. These aerial giants were the largest creatures ever to fly, and they glided over oceans, plains, and forests with unmatched grace. Mammals remained relatively small and unobtrusive during the Cretaceous, but they were evolving in parallel. Early monotremes, marsupials, and placentals appeared during this period, laying the foundation for post-dinosaur terrestrial life. Most mammals were nocturnal and insectivorous, but their brains, senses, and reproductive strategies were developing in ways that would give them an edge in the new world to come. For tens of millions of years, this vibrant planet thrived. Dinosaurs ruled the land, pterosaurs filled the skies, marine reptiles hunted in the oceans, and flowering plants spread across continents. Life was exuberant and resilient, but fragile. And then, at the very end of the Cretaceous, catastrophe struck. About 66 million years ago, a 10-kilometer-wide asteroid slammed into what is now the Yucatan Peninsula in Mexico, creating the Chicxulub crater. The impact released energy equivalent to billions of nuclear bombs, igniting wildfires, causing tsunamis, and launching vast quantities of dust and vapor into the atmosphere. This debris blotted out sunlight for months or even years, causing a global impact winter that collapsed photosynthesis, disrupted food chains, and triggered a sudden and massive extinction event. Alongside the asteroid, massive volcanic eruptions in the Deccan Traps of India may have compounded the environmental stress, adding toxic gases and further warming the planet. The extinction was swift and merciless. Approximately 75% of all species disappeared, including all non-avian dinosaurs, most pterosaurs, marine reptiles like mosasaurs and plesiosaurs, many marine invertebrates, and a vast number of plant and insect species. Only small, adaptable species, including birds, the only surviving dinosaurs, some mammals, and certain reptiles and amphibians, managed to endure. The Cretaceous, then, was both a zenith and an end. It was a period of flourishing beauty, evolutionary brilliance, and ecological complexity, but also the stage for one of the greatest mass extinctions in Earth's history. From the ashes of this cataclysm, new life would rise. The age of reptiles had come to an end, and the age of mammals, of us, was about to begin. The Paleocene epoch marked a profound turning point in Earth's history. It began in the aftermath of catastrophe, a world still trembling from the asteroid impact that ended the reign of the non-avian dinosaurs. The skies had cleared, the fires had died down, and the planet, scarred but still fertile, began to reshape its ecosystems. With the dominant reptiles gone, an evolutionary vacuum had been created. Into this void stepped mammals, birds, and flowering plants, ready to take their place as the primary architects of life on land. The Paleocene was an era of quiet rebuilding and rapid innovation, a world reawakening, slower and more modest than the Cretaceous, but no less important in shaping the path to the modern biosphere. In the immediate aftermath of the extinction, Earth was subdued. The massive die-off had wiped out 3/4 of all species, collapsing food webs and reducing biodiversity to a fragile minimum. But life, as it always does, found a way. Surviving species began to repopulate ecosystems. Small, generalist organisms fared best. Those that could feed on a wide range of resources, reproduce quickly, and adapt to changing conditions. Ferns and fast-growing angiosperms recolonized the barren landscapes. Insects returned in force, becoming once again crucial pollinators and prey. and mammals, which had long hidden in the shadows of dinosaurs, began to emerge as key players in terrestrial life. Mammals during the Paleocene were still relatively small compared to their future forms, but they were beginning to diversify in remarkable ways. These early mammals included insectivores, omnivores, herbivores, and primitive carnivores. Most were no larger than a house cat, yet their rapid evolution set the stage for later giants. Some had adapted to burrowing, others to climbing trees. Certain species began to develop more specialized teeth and digestive systems, enabling them to exploit the expanding variety of plant life. Brain size, too, began to increase, particularly in species that relied on social behavior or problem-solving. One of the most notable trends during the Paleocene was the rise of placental mammals. These animals, which gestated their young for longer periods inside the womb, gave birth to more fully developed offspring than marsupials. This reproductive advantage allowed placentals to spread rapidly and diversify into new ecological niches. Early ancestors of modern hoofed animals, primates, and rodents appeared during this epoch, each lineage setting down roots that would eventually define entire ecosystems. While mammals took the lead on land, birds inherited the skies. With the extinction of the pterosaurs, birds quickly expanded into aerial niches. Many early Paleocene birds were primitive forms, retaining teeth or clawed wings, but they evolved rapidly. Some species grew to enormous sizes in the absence of aerial predators. The now extinct Gastornis, for example, was a giant flightless bird that stood over 2 meters tall and may have been a top predator or scavenger. In coastal and marine environments, seabirds proliferated, feeding on the returning schools of fish and invertebrates. Marine life, though also devastated by the mass extinction, began to rebound. Plankton populations recovered first, re-establishing the base of the oceanic food chain. Mollusks, crustaceans, and bony fish followed, repopulating reefs and coastal waters. Sharks and rays, less affected by the extinction than many marine reptiles, continued to evolve. The once dominant marine reptiles like mosasaurs and plesiosaurs were gone, but new predators were emerging, including early forms of toothed whales and other large fish. Earth's geography during the Paleocene also played a role in shaping life. The continents were continuing their slow drift. South America, Africa, Antarctica, and Australia were still separated from each other and from the northern continents. India was rapidly moving northward toward Asia, a collision that would soon result in the rise of the Himalayas. These movements influenced climate, ocean currents, and species distribution. Vast inland seas had mostly dried up, and the overall climate was warm and humid, supporting lush forests that stretched from the poles to the equator. In fact, the Paleocene was one of the warmest intervals in Earth's recent history. Polar regions, though still dark in winter, were ice-free and vegetated, home to forests filled with mosses, ferns, and conifers. Crocodilians and turtles, animals that require warm climates, thrived even in what are now Arctic and Antarctic latitudes. The lack of ice caps and the high levels of atmospheric carbon dioxide contributed to elevated sea levels, flooding low-lying areas and creating shallow marine habitats along many coasts. Another striking feature of the Paleocene was the development of new ecosystems. Dense tropical forests dominated the equator, while temperate rainforests covered much of the mid-latitudes. Grasses were still rare and had not yet formed extensive plains, so large grassland herbivores had not evolved. Instead, browsing mammals fed on leaves, fruits, and seeds. In the trees, early primates with grasping hands and keen vision were beginning to develop, hinting at the arboreal lifestyle that would characterize many of their descendants. Despite the progress, the Paleocene was not without challenges. The Earth's systems were still fragile, and species turnover remained high. Ecosystems were experimenting, so to speak. Organisms were evolving quickly, but many lineages would rise and fall before establishing any lasting legacy. Predation, Competition and climate fluctuations created a constantly shifting environment in which only the most adaptable species survived. Toward the end of the Paleocene, Earth began to experience another significant shift in temperature. This warming trend culminated in the Paleocene, Eocene thermal maximum, PTM, a dramatic spike in global temperatures driven by massive releases of greenhouse gases. Though technically part of the next epoch, the PTM would have its roots in the slow carbon cycle changes of the late Paleocene, and its effects would reshape the biosphere in dramatic fashion. The Paleocene, in sum, was an era of quiet revolution. Though lacking the titanic creatures of the Mesozoic, it was a crucible of innovation. It laid the evolutionary groundwork for the age of mammals, set in motion the ecological rules that would govern much of the Cenozoic, and witnessed the Earth reclaiming its vibrancy after one of its darkest chapters. It was the dawn of a new kind of world, smaller, perhaps, but more nuanced, and increasingly shaped by the creatures that would one day call themselves human. The Eocene epoch was a time of remarkable warmth, evolutionary experimentation, and dramatic changes in Earth's biosphere. It followed directly on the heels of the Paleocene and inherited a world in transition, a planet shedding the vestiges of its post-extinction recovery and stepping confidently into a new era of mammalian dominance. Over the course of more than 20 million years, the Eocene would witness the rapid expansion of mammals and birds into diverse and complex forms, the transformation of Earth's forests and oceans, and the beginnings of climatic cooling that would lead, eventually, to the modern age. It was a world at once exotic and familiar, alien, and yet a clear stepping stone to the ecosystems we recognize today. At the very start of the Eocene, Earth underwent one of the most extreme global warming events in its history, the Paleocene, Eocene thermal maximum, PTM. This event, possibly triggered by massive methane releases from oceanic hydrates or volcanic activity, caused global temperatures to soar by several degrees Celsius in a geological instant. Polar regions became subtropical, and tropical zones grew even hotter and wetter. The PTM reshaped ecosystems worldwide, triggering extinctions, migrations, and rapid evolution. It profoundly affected ocean chemistry, leading to widespread acidification, and drove many marine species to adapt or perish. This warm climate persisted for millions of years. Ice caps were non-existent, and tropical forests stretched far beyond the equator, reaching into what are now temperate latitudes. Palm trees grew in Alaska, and crocodiles swam in Arctic rivers. The consistent warmth and high humidity supported lush vegetation across much of the planet. Forests blanketed nearly every continent, from dense rainforests in equatorial zones to broadleaf woodlands further north and south. Mammals thrived in this greenhouse world, freed from the ecological dominance of dinosaurs, and helped by the lush vegetation and stable climates. They exploded into a variety of new forms. During the Eocene, many modern orders of mammals emerged for the first time, including early primates, rodents, bats, cetaceans, whales, perissodactyls, odd-toed ungulates like horses and rhinos, and artiodactyls, even-toed ungulates like deer and pigs. These animals were often smaller and more primitive than their modern descendants, but their anatomical innovations laid the groundwork for the mammals of today. Among the most remarkable evolutionary stories of the Eocene is that of whales. Their ancestors had been small, hoofed land mammals, perhaps similar to deer or pigs, that ventured into the water in search of food. Over time, these creatures adapted to aquatic life, developing powerful tails, streamlined bodies, and internalized limbs. By the mid-Eocene, fully aquatic whales like Basilosaurus and Dorodon swam through warm seas. Giant, serpentine creatures with vestigial hind limbs and sophisticated echolocation abilities. These early whales ruled the marine ecosystems that had once been dominated by reptiles. On land, primates began to evolve more complex forms. Early species were small, arboreal, and insectivorous or frugivorous, with large eyes suited for nocturnal vision and grasping hands for climbing. These primates were the distant ancestors of monkeys, apes, and eventually humans. Their development in the dense forests of the Eocene would shape the cognitive and social traits that came to define their lineage. Other mammals took to the skies. Bats made their first appearance, already fully adapted for powered flight and echolocation. These nocturnal hunters quickly became important insectivores, filling the skies over Eocene forests with their agile silhouettes. Rodents, too, diversified rapidly, spreading across continents and evolving specialized teeth for gnawing, an adaptation that would allow them to become one of the most successful mammalian groups in Earth's history. In the oceans, the warm temperatures encouraged high productivity. Coral reefs expanded, fish diversified, and marine mammals like early whales and sea cows flourished. Sharks and rays continued to evolve into new forms. Mollusks and crustaceans rebounded from the late Cretaceous extinction and filled a wide range of ecological niches. Seabirds also diversified, with many adapting to long-distance flight and pelagic hunting. The plant life of the Eocene reflected the warm, humid conditions. Angiosperms, flowering plants, dominated the landscape, forming dense forests filled with broadleaf trees, vines, and understory plants. Insect pollinators like bees, butterflies, and beetles diversified alongside the plants, forming intricate relationships that further accelerated plant evolution. Fungi, mosses, and ferns thrived in the humid undergrowth, contributing to the rich biodiversity of Eocene forests. Toward the middle of the epoch, however, Earth began to cool. This shift was gradual but significant. It was driven by a combination of tectonic activity, changing ocean currents, and declining atmospheric carbon dioxide levels. The Indian subcontinent continued its collision with Asia, triggering the uplift of the Himalayas, a process that began altering global weather patterns and carbon cycling. The formation of the Antarctic Circumpolar Current, as Antarctica drifted further south and separated from South America and Australia, isolated the continent and allowed ice sheets to begin forming at its pole. This cooling trend led to a drying of the global climate, with some forests thinning and grass-like plants beginning to expand in certain regions. Mammals had to adapt once again. Larger body sizes became more common, possibly as a way to conserve heat. Some species began to exploit more open habitats, setting the stage for the grassland ecosystems that would flourish in the next epoch. Birds also evolved rapidly during the Eocene, with many modern groups appearing for the first time. Raptors, waterfowl, shorebirds, and songbirds emerged in recognizable forms. Some species, such as the massive flightless Gastornis, continued to dominate certain terrestrial niches, but the era of giant predatory birds was slowly giving way to more agile and diverse avian life. By the end of the Eocene, the world had changed dramatically. The exuberant warmth of the early epoch had given way to a cooler, more seasonal world. Faunal turnover increased, with several groups of mammals and birds going extinct or being replaced by better adapted forms. Forests began to retreat from the poles, and the earliest open woodlands and savannas emerged in some regions. Life, once again, was learning to adapt to a cooler, drier, and more dynamic Earth. The Eocene was a bridge between the chaotic recovery of the Paleocene and the more structured ecosystems of the modern world. It was a time of innovation, of mammalian ascendancy, of evolutionary risk and reward. In its warm forests, in its shallow seas, in its cooling mountains, the future was being written, one mutation, one migration, one survival at a time. The Oligocene epoch marked a time of global transformation, a distinct shift away from the lush, greenhouse world of the Eocene and toward the cooler, drier climates that would eventually characterize the modern Earth. Spanning roughly 11 million years, the Oligocene was a period of cooling temperatures, declining atmospheric carbon dioxide, and the continued movement of continents into their current configurations. These changes dramatically reshaped ecosystems, drove the extinction of some ancient lineages, and opened the door for the rise of new, highly specialized species, particularly among mammals and plants. The world was becoming more open, more seasonal, and increasingly defined by the complex relationships between climate, tectonics, and evolution. One of the defining characteristics of the Oligocene was its continued global cooling. This climatic trend had begun near the end of the Eocene, but during the Oligocene it accelerated. Antarctica, now fully isolated by the Southern Ocean, developed permanent ice sheets for the first time in tens of millions of years. This marked the beginning of the modern polar climate and caused global sea levels to drop. Ocean circulation patterns changed dramatically, leading to greater thermal stratification in the oceans and a reorganization of marine ecosystems. The drop in temperature and precipitation had widespread effects on terrestrial habitats. The expansive tropical forests of the Eocene retreated toward the equator, replaced by open woodlands, shrublands, and the first true grasslands in many areas. These new, more open environments favored animals that were fast, agile, and capable of covering large distances in search of food and water. As a result, mammalian evolution during the Oligocene entered a new phase, one marked by speed, endurance, and specialization. The rise of grasslands was a quiet revolution. Grasses had existed for millions of years, but had remained minor components of most ecosystems. Now, in the cooler, drier world of the Oligocene, they began to dominate large swathes of land. Grasses are uniquely adapted to grazing pressure. They grow from the base rather than the tip, allowing them to survive being eaten repeatedly. This adaptation opened the door for the evolution of grazing animals and created feedback loops between herbivores and vegetation that would reshape Earth's landscapes. In response to the spread of grasslands and open habitats, many herbivorous mammals evolved new body forms and dental adaptations. High-crowned teeth became more common, capable of withstanding the wear caused by chewing tough, silica-rich grasses. Limbs lengthened, and body plans shifted toward more cursorial, running-adapted forms. Horses, in particular, underwent rapid diversification during the Oligocene. The ancestors of modern horses were small, forest-dwelling browsers, but by the end of the epoch, they had begun evolving into larger, faster grazers with single hooves. Other ungulates, hoofed mammals, also thrived. Rhinoceroses diversified into both large and small forms. The giant Paraceratherium, possibly the largest land mammal to ever live, roamed the plains of Asia during this time. Camels, deer, pigs, and early antelopes appeared in various parts of the world, each adapting to local conditions. Artiodactyls, even-toed ungulates, and perissodactyls, odd-toed ungulates, became dominant herbivores in many regions, setting the stage for their success in later epochs. Predatory mammals followed suit, adapting to hunt the growing populations of large, mobile prey. The creodonts, once dominant predators, began to decline, while true carnivores, the ancestors of modern cats, dogs, bears, and others, rose to prominence. These new predators had sharper senses, more efficient body structures for chasing prey, and increasingly complex hunting strategies. Packs, stealth, and speed became evolutionary advantages, leading to the development of many familiar predatory behaviors. Primates also evolved during the Oligocene, although their story was quieter than that of the ungulates and carnivores. In Africa and Asia, early monkeys and apes began to diversify. These primates lived in the shrinking forests and woodlands, relying on arboreal skills, social behaviors, and keen vision to thrive. The lineage that would eventually lead to humans had not yet split off, but the roots of that branch were beginning to form. Marine ecosystems, too, were evolving. With the establishment of modern ocean currents and temperature gradients, plankton populations changed, which in turn affected the entire marine food web. Mollusks, bony fish, and crustaceans adapted to new conditions, while whales underwent a second major radiation. The earliest toothed and baleen whales diversified, exploiting different feeding strategies, some hunting squid and fish with echolocation, others filtering krill and plankton in massive gulps. Sea cows and seals also evolved and began to populate coastal waters. Birds continued to diversify alongside mammals. Waterfowl, raptors, and songbirds appeared in more recognizable forms, adapting to the increasingly varied habitats. Large, flightless birds continued to exist in some isolated regions, often as apex predators or herbivores, though they were becoming rarer as mammalian carnivores became more efficient. On a tectonic level, the continents continued to drift toward their modern positions. The Atlantic Ocean widened, and the collision between Africa and Europe created mountain ranges and inland seas that shaped local climates and migration routes. The collision of the Indian Plate with Asia continued to uplift the Himalayas, intensifying monsoon patterns and altering global climate systems. South America remained isolated, leading to the evolution of unique fauna, including early sloths, anteaters, and marsupials. Floral diversity was high during the Oligocene, though vegetation patterns shifted with the climate. Deciduous forests replaced some tropical forests in higher latitudes, and coniferous forests expanded in cooler regions. The dominance of angiosperms continued, and their partnership with insect pollinators deepened. Insects such as bees, butterflies, and beetles evolved in tandem with flowers, supporting complex pollination networks that ensured the continued success of flowering plants. The Oligocene ended with further cooling and drying, a continuation of the long-term trend that would ultimately lead to the ice ages of the Pleistocene. Yet it was also a time of tremendous innovation, laying the foundation for the modern biosphere. The world was not yet what we know today, but it was beginning to resemble it. Grasslands stretched further each year. Mammals were rising not just in number, but in ecological complexity. And life, as always, was adapting, shaped by the changing winds, the drifting continents, and the slow, relentless hand of time. The Miocene epoch was a pivotal chapter in Earth's history, a time of climatic transformation, continental realignment, and extraordinary evolutionary radiation. Spanning nearly 18 million years, it was during the Miocene that the modern world truly began to take shape. Mammals and birds diversified to fill newly emerging ecological niches. Grasslands spread widely across the continents, and primates, especially the great apes, began evolving traits that would eventually culminate in the rise of humans. The landscapes and life forms of the Miocene would become increasingly recognizable, not only in structure, but also in behavior and ecology. It was a time of motion, transition, and definition. At the heart of the Miocene was a continued cooling trend that had begun in the Eocene and Oligocene. Although there were fluctuations, the general trajectory of Earth's climate moved toward greater aridity and seasonality. Forests continued to retreat in many areas, replaced by woodlands, savannas, and open grasslands. This transformation wasn't uniform across the globe, but where it occurred, it fundamentally altered the way animals lived and moved. Herbivores adapted to longer migrations, faster sprints, and more efficient digestion of fibrous, silica-rich grasses. Carnivores, in turn, became sleeker, faster, and more specialized in their strategies for capturing prey. The Miocene saw the peak of mammalian diversity in many groups. Hoofed mammals dominated the open plains. Horses, antelope, deer, camels, and rhinoceroses were all present in large numbers and forms. Horses in particular underwent rapid evolution. From multi-toed forest dwellers, they became single-toed, high-crowned, fast-running grazers, fully adapted to life on expansive grasslands. This same pattern repeated itself across ungulate groups: longer limbs, complex teeth, and efficient locomotion. Among the predators, large cats began to appear in recognizable forms, alongside hyenas, canids, early dogs, and bear-like carnivores. These animals competed for dominance in a world where chasing prey across long distances was now as important as stealth and ambush. Pack behavior became more common among certain groups, improving hunting efficiency and laying the groundwork for complex social behavior. Scavengers also adapted, with vultures and hyenas evolving specific traits for locating and consuming carrion before competitors could. One of the most dramatic events of the Miocene was the continued uplift of major mountain ranges. The collision of the Indian and Eurasian plates further pushed up the Himalayas, altering atmospheric circulation and intensifying the Asian monsoon. In the Americas, the Andes rose along the western edge of South America, while the Rockies continued to shape the North American interior. These geologic forces didn't just change topography. They influenced rainfall patterns, ocean currents, and the very pace of biological evolution by creating new habitats and barriers to migration. Marine ecosystems also experienced significant change. Ocean temperatures cooled, promoting the upwelling of nutrients and supporting massive blooms of plankton. This in turn fed entire chains of marine life, from tiny fish to great whales. Modern cetaceans, dolphins, porpoises, and baleen whales underwent explosive diversification during the Miocene. Some species grew to immense sizes, using baleen to filter krill and small fish in vast quantities. Sharks, too, flourished, including the infamous megalodon, one of the largest predatory fish to ever live. The oceans of the Miocene teemed with life, complex food webs, and constant evolutionary experimentation. Among terrestrial life, primates were undergoing a quiet but crucial transformation. Forested regions in Africa and Eurasia still supported a variety of monkeys and apes. Miocene apes were particularly diverse, with dozens of genera inhabiting tropical woodlands, each adapting in different ways to diet, locomotion, and social life. This was the age of Proconsul, Dryopithecus, Civipithecus, and other early apes, some of which show a mix of traits linking modern apes and early hominins. These Miocene apes occupied a wide range of habitats, from densely forested canopies to more open woodland fringes. Some began experimenting with more upright forms of locomotion, an adaptation that may have eventually led to bipedalism. While no definitive human ancestors are known from the early Miocene, the evolutionary groundwork was being laid in this epoch. Environmental pressures like shifting forest boundaries and changing diets nudged primates toward more flexible, adaptive behaviors. Increased brain size, tool use, and social cooperation were not yet dominant traits, but the conditions that would eventually favor them were now beginning to emerge. Plants also played a critical role in the Miocene story. The spread of grasses led to major shifts in floral composition. Grasslands became complex ecosystems, hosting not only grazing mammals but also the insects, birds, and small mammals that thrived in the niches grasslands offered. Trees became more drought-tolerant in many regions, and fire became a regular ecological force, influencing plant succession and the shape of ecosystems. Flowers and insect pollinators continued their coevolution, with bees, butterflies, and other pollinating insects diversifying to match the new floral landscapes. Birds adapted to these changing habitats, too. Many modern bird families appeared during the Miocene, including crows, finches, owls, and hawks. Some species became specialists in open country hunting, while others adapted to life alongside large grazing animals. Waterfowl, waders, and songbirds also diversified, taking advantage of the mosaic of lakes, rivers, wetlands, and grasslands spreading across the continents. South America remained a land apart during much of the Miocene, isolated from the northern continents by ocean barriers. This isolation led to the evolution of bizarre endemic fauna: giant flightless predatory birds, strange hoofed mammals with features of both rhinos and camels, and early forms of armadillos and sloths. It wasn't until the very end of the Miocene, and into the following epoch, that the Isthmus of Panama began to form, eventually bridging North and South America and setting the stage for one of the greatest biogeographic exchanges in Earth's history. As the Miocene drew to a close, global temperatures began to fall even further. Glaciers expanded in the southern hemisphere, and polar ice increased. Forests continued to contract, and open habitats became increasingly dominant. This environmental pressure favored animals capable of adapting to seasonal climates and dynamic ecosystems. The world was preparing for an even cooler future, a future marked by ice ages, megafauna, and, eventually, the emergence of hominins capable of changing the world not just by evolving, but by thinking. The Miocene was a forge. It shaped the creatures, the landscapes, and the climate systems that would define Earth for millions of years to come. It marked the beginning of the modern age, not by sudden change, but by the slow accumulation of transformations, each one paving the way for what was next. The Pliocene epoch was a bridge between worlds, between the lush, teeming ecosystems of the Miocene and the stark, challenging environments of the ice ages that would soon follow. Lasting nearly 3 million years, the Pliocene was marked by continued cooling, drying, and tectonic reshaping of Earth's surface. It was during this time that many modern species began to emerge in recognizable forms. Ecosystems began to resemble their current configurations, and the earliest members of the human lineage took their first steps on 2 feet. Though not as dramatic as the mass extinctions of earlier epochs, the Pliocene was a time of quiet, relentless transformation, preparing the stage for the arrival of humanity. Climate continued its long descent into cooler conditions during the Pliocene. Polar ice caps expanded, particularly in the northern hemisphere, and the global climate grew increasingly seasonal. Tropical and subtropical forests shrank, giving way to savannas, woodlands, and grasslands in many regions. These new environments favored organisms that could cope with unpredictability, animals capable of migrating, adapting, and surviving on variable diets. One of the most important geological events of the Pliocene was the final closure of the Central American Seaway. Over millions of years, tectonic forces had been raising the Isthmus of Panama, and by the mid-Pliocene, the land bridge between North and South America was fully formed. This single event had profound implications for both marine and terrestrial life. Ocean currents were drastically altered, with the newly formed Gulf Stream carrying warm water northward and accelerating glaciation in the Arctic. At the same time, the so-called Great American Biotic Interchange began. Animals from North and South America crossed into new territories, often with dramatic consequences. South America, having evolved in isolation for tens of millions of years, saw the arrival of new predators and herbivores from the north: bears, cats, deer, horses, and others. In turn, native South American animals like armadillos, possums, and terror birds moved north. The mixing of these faunas led to intense ecological competition, extinction, and adaptation. While some North American species thrived in their new southern environments, many of South America's unique animals struggled to compete and survive. In Africa, the Pliocene was the crucible in which the human lineage began to differentiate itself. As forests retreated and savannas expanded, early hominins adapted to life on the ground. Walking upright, bipedalism, offered numerous advantages in open environments: better visibility for spotting predators, more efficient locomotion over long distances, and the ability to carry tools, food, or infants. Fossil evidence from this epoch includes numerous early human ancestors, such as Australopithecus afarensis, a species known from the famous Lucy skeleton. These early hominins were still small-brained compared to modern humans, but they exhibited increasing behavioral complexity. Some may have used rudimentary tools, scavenged meat, or even coordinated in social groups for defense and foraging. The Pliocene did not witness a dramatic cognitive leap, but it did witness the slow accumulation of traits that would eventually make such a leap possible. Changes in diet, brain structure, and social behavior were quietly evolving under the pressures of an ever-shifting environment. Elsewhere in the world, mammalian life continued to diversify in response to open habitats. Herd animals such as antelope, horses, and camels became more prevalent, adapting to fast movement across flat terrain. Predators followed suit, with large cats, canids, and hyenas evolving powerful limbs and sharp senses to track prey. In Asia and Europe, elephants and their relatives roamed in increasing numbers, with species like the massive Mammuthus meridionalis foreshadowing the woolly mammoths of the coming ice ages. Marine life was also adapting to the new configuration of oceans and coastlines. With the rise of the Isthmus of Panama, the Atlantic and Pacific marine populations were permanently divided, evolving in isolation from each other. In the cold southern waters, pinnipeds such as seals and sea lions thrived, while cetaceans, whales, and dolphins continued their complex evolutionary dance in every ocean. Coral reefs began to shift to new latitudes in response to changing temperatures, and shellfish and fish communities evolved to meet the needs of new predators and prey. Plant life during the Pliocene followed the trend toward aridity and seasonality. Grasslands spread to dominate much of the planet's interior regions, particularly in Africa, Eurasia, and North America. Grasses became the backbone of entire ecosystems, feeding everything from insects to elephants. Trees and shrubs adapted to drier, more variable conditions, while fire became a common ecological force, shaping plant communities and favoring fire-resistant species. Birds diversified alongside the mammals, with many species evolving to fit into the newly expanding niches of grassland and open woodland. Ground-nesting birds, large flightless birds, and scavengers all thrived. In North America, the giant Titanes walrus, a descendant of South American terrorbirds, roamed the grasslands, a relic of the continent's pre-human predators. Geologically, the Pliocene was a period of settling into a new normal. Mountain ranges continued to rise slowly, especially the Himalayas and Andes, driving further changes in weather patterns. Volcanic activity persisted in many parts of the world, reshaping local landscapes and influencing climate at regional scales. Glacial cycles, still in their infancy, began to establish the rhythm that would dominate the coming Pleistocene. Toward the end of the Pliocene, the first real pulses of glaciation began in earnest. Ice sheets spread across parts of the northern hemisphere, particularly in North America and Eurasia. These glacial advances and retreats would become the dominant force shaping Earth's surface and life during the Pleistocene. River valleys were carved deeper, sea levels fluctuated, and organisms had to adapt to the growing instability of their environments. In this context of change and uncertainty, life continued its steady march forward. Many modern animal genera and even species emerged during the Pliocene. The Earth, while still wild and untamed, now looked more like the world we know. Its mountains, oceans, forests, and grasslands largely familiar, its creatures increasingly recognizable. The Pliocene was not a time of explosive change, but of quiet establishment. It was the final tuning of the planet's ecosystems before the dramatic climatic swings of the Ice Age. And somewhere on the savannas of Africa, A small group of upright primates was about to begin a journey that would ultimately reshape the planet itself. The Pleistocene epoch was a time of relentless extremes, of towering ice sheets and vast frozen landscapes, of shifting continents and ceaseless migrations, of titanic beasts and the earliest footsteps of humanity. Spanning over 2 million years, the Pleistocene witnessed the rise of glaciers and the fall of giants. It was an age defined by ice, but more than that, it was the stage upon which the most significant drama in Earth's history began to unfold. The emergence of Homo sapiens and the dawn of human culture, technology, and survival on a planet gripped by cold. At the heart of the Pleistocene were the glacial-interglacial cycles, massive climatic shifts that caused ice sheets to advance and retreat across the globe. Driven by subtle changes in Earth's orbit and tilt, these cycles occurred roughly every 100,000 years, plunging much of North America, Europe, and Asia under kilometers of ice during glacial maxima. Between these freezes, warmer interglacial periods allowed forests to return, rivers to swell, and life to surge once more. Sea levels fluctuated by over 100 meters between extremes, exposing land bridges such as Beringia between Asia and North America, and Sundaland between mainland Asia and the islands of Indonesia. These land bridges played a crucial role in the movement of species. Mammals migrated across continents, chasing food and shelter in the face of changing environments. Humans, too, followed the paths revealed by the receding seas, expanding from Africa to the rest of the world. In fact, it was during the Pleistocene that humanity truly began to disperse. Homo erectus, Homo heidelbergensis, Homo neanderthalensis, and finally Homo sapiens all roamed the earth during this epoch, their migrations, interbreeding, and extinctions forming a tangled but vital evolutionary web. The landscapes of the Pleistocene were in constant flux. Ice sculpted the land wherever it touched, scraping valleys, grinding mountains, and flattening vast plains. In the temperate zones just south of the glaciers, grasslands and tundra supported enormous herds of herbivores. Mammoths, woolly rhinoceroses, steppe bison, musk oxen, giant elk, and ground sloths. These megafauna dominated the ecosystems of the epoch, their immense size and adaptation to the cold climates and vast, open spaces. Their predators were equally impressive: cave lions, saber-toothed cats, dire wolves, short-faced bears, and packs of hunting humans. In Africa, where ice never dominated but climates still shifted, ecosystems alternated between savanna, forest, and desert. Here, early humans evolved in dynamic environments that demanded flexibility, cooperation, and tool use. The fossil record reveals a steady progression in brain size, posture, and technology, from Australopithecus to Homo habilis, Homo erectus, and finally to anatomically modern humans. Stone tools became more refined, fire was mastered, clothing and shelter were developed, and eventually, art, burial, and symbolic thought began to appear. The presence of humans gradually transformed ecosystems. Though small in number, our ancestors were persistent hunters, gatherers, and later organizers of complex societies. They learned to exploit their environments with increasing skill, building tools from flint, bone, and antler, tracking herds across continents, and cooperating in ways that no other species could match. They formed languages, mythologies, and oral traditions, passing knowledge from one generation to the next in ways that transcended mere instinct or imitation. The Pleistocene was also a time of extinction. As the climate oscillated and humans expanded, many large animals began to disappear. Whether due to human overhunting, rapid climatic shifts, disease, or a combination of these factors, entire species vanished from the Earth. North America lost its mammoths, mastodons, giant ground sloths, and saber-toothed cats. Australia saw the extinction of giant marsupials like Diprotodon and the fearsome Megalania lizard. Europe lost its woolly rhinoceroses, cave bears, and straight-tusked elephants. This wave of megafaunal extinction accelerated in the last 40,000 years of the epoch, overlapping with the spread of Homo sapiens across the globe. As the Pleistocene neared its end, Earth entered its last major glacial maximum, peaking around 21,000 years ago. Ice sheets reached their farthest extent, and global temperatures plummeted. In this harsh world, humans adapted in remarkable ways. They built shelters from bone and hide, sewed garments from furs, and created detailed cave paintings that hinted at rich inner worlds of belief and imagination. They domesticated dogs, perhaps their first allies in the struggle to survive, and began experimenting with plant cultivation and animal taming, laying the groundwork for what would come next. Then, slowly, the ice began to retreat. Around 12,000 years ago, temperatures began to rise, glaciers melted, and sea levels rose. Forests returned to Europe and North America. Deserts shifted in Africa and Asia, and the stage was set for a radical change in how humans lived. No longer solely hunters and gatherers, they would begin to settle, build, and plant. The Pleistocene was ending, and the Holocene, the epoch of civilization, was about to begin. But the legacy of the Pleistocene remains etched into the surface of the Earth and embedded deep within us. The Holocene epoch represents a radical shift in the history of Earth, not just in terms of climate and ecology, but in the nature of life itself. Lasting just a fraction of geological time, it encompasses the entire arc of human civilization. In these mere 11,500 years, the planet has transitioned from the last vestiges of the Ice Age to a world utterly transformed by the activities of one species, Homo sapiens. The Holocene is the age of agriculture, of cities, of industry, and of the Anthropocene's shadow looming ever larger. It is the moment when the Earth, long shaped by tectonics and evolution, began to be reshaped by intention, ambition, and technology. As the last glacial period ended, global temperatures began a steady rise. Massive ice sheets that had blanketed North America, Europe, and Asia melted, sending torrents of fresh water into the oceans and dramatically raising sea levels. Coastlines retreated inland, revealing the final contours of modern continents. Lakes and rivers filled, forests expanded into previously frozen regions, and deserts like the Sahara briefly bloomed with vegetation. This warming was not uniform. Regional variations in climate produced unique conditions, but overall, the Earth entered a relatively stable, warm phase that allowed ecosystems to flourish and humans to thrive. The most profound development of the Holocene was the agricultural revolution. In the Fertile Crescent of the Middle East, and independently in other parts of the world such as China, Mesoamerica, and the Andes, humans began to domesticate plants and animals. Wheat, barley, rice, maize, potatoes, cattle, sheep, goats, pigs. These once wild species became staples of human life. Agriculture allowed humans to settle, to store surplus food, and to grow populations in ways that had never before been possible. With agriculture came villages, then towns, and eventually cities. The first civilizations rose along great rivers: the Nile, the Tigris and Euphrates, the Indus, the Yellow. These early societies developed writing, law, organized religion, trade networks, and social hierarchies. They constructed temples and monuments that still stand millennia later. They charted the stars, measured time, and began to see themselves not just as part of nature, but as its stewards, or its masters. This shift had vast ecological consequences. Forests were cleared to make room for crops. Animals were hunted or domesticated, driving some to extinction. Wetlands were drained, rivers diverted, and soils cultivated repeatedly. The natural world, which had evolved over millions of years, was suddenly subject to the rapid, cumulative impacts of culture. Human beings, though still subject to drought, flood, and disease, had begun to push back against nature's constraints. Climate in the Holocene remained relatively stable, but not without variation. The Younger Dryas, a brief return to near-glacial conditions at the beginning of the epoch, was followed by the Holocene thermal maximum, a period of warmth that allowed forests to spread far north. Later came the medieval warm period and the Little Ice Age, both of which had profound effects on agriculture, population, and migration. Yet none of these shifts matched the drama of the Pleistocene glaciations. Compared to the previous epoch, the Holocene was a time of relative calm. That calm, however, allowed for complexity. Societies became more interconnected. Empires rose and fell. Technologies developed at an accelerating pace: metallurgy, navigation, printing, engines, electricity. The world became smaller as exploration and colonization tied distant lands together through commerce and conquest. Human history, once defined by subsistence and survival, became a story of innovation, conflict, and increasingly, environmental impact. By the time of the Industrial Revolution in the 18th century, the Holocene entered a new phase. Fossil fuels, coal, oil, natural gas, were harnessed to power machines, factories, and transport. Populations exploded. Cities expanded. Landscapes were transformed on an unprecedented scale. Air, water, and soil began to bear the marks of pollution. The greenhouse gases released during this period began to alter Earth's climate once again, this time not by natural cycles, but by human activity. In the 20th and 21st centuries, the pace of change accelerated even more. Technology digitized the world. Global trade and communication made the planet more interconnected than ever. Nuclear weapons gave humanity the power to destroy itself. Antibiotics and vaccines extended lifespans. Space exploration began. And yet, alongside these achievements, came profound challenges. Biodiversity plummeted. Ecosystems were degraded. The climate warmed faster than at any time in the past several million years. Sea levels rose, ice caps melted, and extreme weather events grew more frequent and destructive. Many scientists now argue that we have entered a new epoch, the Anthropocene. Though not officially recognized as part of the geological timescale, the Anthropocene is proposed as a successor to the Holocene, a reflection of the fact that human activity now shapes the Earth's geology, climate, and biosphere more than any natural force. The markers of this new age are unmistakable. Plastic in the oceans, concrete in the soil, radioactive isotopes from nuclear tests, and carbon dioxide levels not seen in millions of years. Still, we remain within the Holocene in the official geological record, and within it lies the totality of what we call history: the rise of civilizations, the sweep of cultures, the turning of empires, and the birth of modernity. It is an epoch that demonstrates the extraordinary capacity of one species to adapt, to build, to destroy, and perhaps to heal. Whether the Holocene is remembered as a fleeting calm before catastrophe, or as the age when humanity began to live in harmony with its planet, remains to be seen. The Anthropocene is not yet an officially recognized epoch in the geological timescale, but its influence is undeniable. Proposed to begin in the mid-20th century, this epoch is defined not by tectonic upheavals or natural climatic cycles, but by the overwhelming global impact of one species, Homo sapiens. For the first time in Earth's 4.5 billion year history, a single species has become a planetary force, altering the atmosphere, oceans, biosphere, and even the geological record itself. The Anthropocene is not simply a continuation of the Holocene. It is a rupture, a new geological chapter marked by rapid, human-driven transformations on a global scale. The mid-20th century was chosen by many scientists as the likely starting point of the Anthropocene for a simple reason: the Great Acceleration. This was the post-World War II era in which nearly every metric of human activity — population growth, fossil fuel consumption, industrial output, urbanization, plastic production, chemical usage, and greenhouse gas emissions — began to rise exponentially. This sudden burst of activity left visible, measurable marks on the planet. Atmospheric CO2 levels surged. Microplastics began accumulating in marine and terrestrial sediments, and nuclear weapons testing deposited a global layer of radioactive isotopes, now detectable even in the deepest ice cores and most remote soils. Geologists typically define epochs by distinctive strata, layers of rock or sediment containing unique chemical or biological signatures. The Anthropocene provides several such markers. Artificial materials such as plastics, aluminum alloys, concrete, and fly ash from coal combustion now appear in layers of sediment across the Earth. These materials did not exist in nature before humans created them. In some places, especially in riverbeds, lakes, and coastal sediments, these synthetic markers are already forming new kinds of rock, technofossils, evidence of our species' industrial legacy. But the Anthropocene is not just a story of geology. It is also a story of profound ecological change. Humans have reshaped the biosphere more radically than any natural event in the last tens of millions of years. Over 75% of the Earth's ice-free land has been altered by agriculture, urban development, or infrastructure. More than 1 million species are currently threatened with extinction due to habitat loss, pollution, climate change, and overexploitation. The sixth mass extinction, driven not by asteroids or volcanism, but by deforestation, industrial fishing, and invasive species, is now underway. Climate change stands as the most defining feature of this proposed epoch. Driven by the burning of fossil fuels, the buildup of greenhouse gases in the atmosphere has caused global average temperatures to rise more than 1 degree Celsius above pre-industrial levels. This warming has triggered a cascade of effects: melting glaciers and polar ice caps, rising sea levels, longer droughts, more frequent wildfires, and intensifying storms. The Arctic is warming nearly 4 times faster than the global average. Coral reefs, which support vast marine ecosystems, are bleaching and dying at alarming rates. These shifts are no longer predictions. They are measurable, observable, and accelerating. The Anthropocene has also transformed the water cycle. Massive dams, irrigation systems, and water diversion projects have altered the flow of rivers and changed freshwater availability for billions of people. Groundwater reserves are being depleted faster than they can be replenished. Oceans are not only warming, they are becoming more acidic due to carbon absorption, threatening marine life at a foundational level. Coastal erosion, algal blooms, and declining fish stocks are reshaping human economies and food systems. In the atmosphere, air pollution from industrial and transportation sources kills millions of people annually, while the thinning of the ozone layer, now slowly healing, was a stark warning of how vulnerable the planet's systems are to human influence. Space itself has not been spared. Thousands of satellites and tons of space debris now orbit Earth, creating a technological shell that is as much a part of the modern Earth system as the biosphere or lithosphere. Human societies, too, have become entwined with these environmental shifts. Food production, once the foundation of civilization, is under pressure from soil degradation, water scarcity, and extreme weather. Mass migrations are increasingly driven by climate-related disasters and resource conflicts. Inequality has deepened, with the most vulnerable populations often suffering the worst impacts of environmental collapse they did little to cause. Yet, amid this crisis, a global awareness has emerged, a recognition that the future of civilization and the health of the planet are inseparable. Technological responses have grown in ambition. Renewable energy is expanding rapidly, with solar and wind power offering alternatives to fossil fuels. Electric vehicles, smart grids, and carbon capture are being developed to mitigate emissions. Global treaties, like the Paris Agreement, aim to unify nations in reducing climate impacts, though progress remains inconsistent. Reforestation efforts, conservation programs, and sustainable agriculture initiatives reflect a growing movement to restore ecological balance. The Anthropocene is also cultural. It has entered art, literature, philosophy, and politics. It forces us to confront fundamental questions. What does it mean to be human in an era when our choices determine the fate of the planet? How do we live ethically on a world where every action has global consequences? The Anthropocene is not just a geological epoch. It is a moral and existential turning point. Whether the Anthropocene becomes officially recognized or not, its reality is indisputable. Earth will carry the marks of this age for millions of years to come. The sediments, the extinction records, the carbon spikes, the plastic layers. These will speak to future geologists of a time when a clever primate species took the planet's reins. Whether it steered into collapse or transformation remains the story still being written. The story of Earth does not end with the Anthropocene. As with all epochs before it, this one, too, will eventually give way to something else. The future of our planet is an unfolding narrative, shaped by forces both ancient and newly born. Tectonic plates will continue to drift. The climate will continue to shift. Life will adapt, evolve, disappear, and re-emerge. But unlike any time in the planet's history, the direction of these changes now hinges, at least in part, on the decisions of one species. The trajectory of Earth's future, for the first time, is not solely a function of natural processes. It is also a product of culture, politics, science, and imagination. In the short term, centuries to a few thousand years, Earth will continue to respond to the disruptions introduced during the Anthropocene. If greenhouse gas emissions are not curtailed, global temperatures may rise by 2 to 4 degrees Celsius or more above pre-industrial levels, with dramatic consequences. Coastal cities could be submerged by rising seas. Entire ecosystems may collapse under the strain of heat, drought, or acidification. Agriculture, water availability, and habitability could shift in ways that force massive migrations and political upheavals. Tropical regions may become unlivable for hundreds of millions of people. At the same time, technological progress may offer mitigation, carbon capture, climate engineering, or even breakthroughs in clean energy that help stabilize the planet. Still, no technological fix comes without risk. Geoengineering projects, such as injecting aerosols into the stratosphere to reflect sunlight, may have unintended consequences for global rainfall or atmospheric circulation. Ecosystems altered by human hands may not respond as expected. The future of Earth will likely be one of complex interplays between remediation and consequence, between invention and restraint. Looking further ahead, tens of thousands to millions of years, the planet will move on. Even if humans disappear tomorrow, the carbon already released into the atmosphere will linger for millennia. Ice sheets will take thousands of years to fully respond. Sea levels could remain high for tens of thousands of years, redrawing coastlines and reshaping continental margins. Coral reefs may require millions of years to recover, if they ever do. Extinct species will not return, but new ones will evolve. Life will find its way, as it always has. Plate tectonics will continue to remodel Earth's surface. Continents will merge again into new supercontinents, perhaps a Pangea Proxima, some 250 million years from now. Mountains will rise and erode. Ocean basins will open and close. Volcanism will continue to renew and destroy. Earthquakes will still shake cities, though those cities may be long gone. The Earth, in its deep rhythms, does not rush. Astronomical cycles will also shape the future. In roughly 50,000 years, Earth's axial tilt and orbital shape will again bring glaciation. A new ice age is expected, unless human-driven warming delays or cancels it. In 500 million years, the sun's increasing luminosity may begin to destabilize Earth's climate, making it hotter and less habitable. In about 1 to 1.5 billion years, rising temperatures may boil away the oceans entirely. Photosynthesis could cease, and the biosphere as we know it may collapse. By then, Earth could resemble the hot, desolate surface of Venus. And yet, the greatest variable in Earth's future is human civilization. If we endure, if we transition to sustainable technologies, stabilize the climate, and adapt to the pressures we have created, then our story may be one of resilience rather than ruin. In the distant future, humans may spread beyond Earth, establishing habitats on Mars, the Moon, or even exoplanets. In such scenarios, Earth becomes not just a cradle, but a cultural and ecological origin point, a revered and protected planetary home. Alternatively, if we fail to avert ecological collapse, the Earth will recover without us. It has done so many times. After the Permian extinction, life took 10 million years to rebound. After the asteroid that killed the dinosaurs, mammals and birds quickly filled the vacant ecological roles. In the wake of any human-caused extinction, evolution will again experiment, diversify, and explore. The scars will heal, slowly but surely. One day, far beyond our own existence, Earth itself will perish. In about 5 billion years, the Sun will expand into a red giant, likely engulfing Mercury and Venus, and perhaps Earth. Even if our planet survives this phase, it will be scorched, sterilized, and lifeless. Eventually, the Sun will shed its outer layers, becoming a white dwarf, and Earth, if it still exists, will orbit a cold, dim remnant of the star that once gave it life. The solar system will continue to drift through the galaxy. Earth will be a relic, its rocks and craters holding ancient secrets of oceans and creatures long gone. But even that is not the end. Given enough time, gravitational interactions may fling Earth out of the solar system entirely. Or, billions of years from now, it may collide with another body, be absorbed into a neutron star, or be shattered in a galactic event. Every atom of Earth will eventually return to the cosmos, scattered across space, recycled into stars, planets, or perhaps new life. So the story of Earth is, at its core, a cosmic one. Born of stardust, forged by gravity, tempered by fire and water, shaped by time, and transformed by life. It has endured bombardments, ice ages, extinctions, and revolutions. It has hosted trilobites and tyrannosaurs, forests and deserts, volcanoes and glaciers, and now, people who wonder about its fate. The future of Earth is not fixed. It is a path that forks with every choice we make. We may write ourselves into its future for millennia to come, or we may vanish and leave the planet to tell its own story once again. Either way, Earth will continue. It always has. It always will.